Hello guys, welcome back to my YouTube channel. So today I'm going to start Vectorless RAG. So in this video we are going to build a complete RAG system without using embedding, without any vector database, and without spending a single rupee on API. Yes, you heard that right. Okay, so most tutorial will tell you that you need a vector database and expensive embedding model to build RAG, but that's not always true. In this video, I will show you a simple and extremely powerful approach called the vector RAG, where we use BM25, a classical search algorithm used by real world system like Elasticsearch. So by the end of this video, you will understand what is RAG actually, what is RAG actually is, and second, how retrieval works without embedding, and third, how to build your own working RAG pipeline from scratch. So let's get started. So here what we will cover step by step. So first we will understand what problem RAG solve and why it needed. Then we will compare traditional vector-based RAG with vectorless RAG, so you clearly understand the difference. After that, we will build our knowledge base, which is basically the data or system will search through. Then we will implement RAG 25 from scratch, so you actually understand how retrieval work internally. Once that done, we will build the retriever and see how the document are ranked. Okay, finally we will connect everything into a full RAG pipeline and test it with the real query. So by the end, you will have a complete working system, not just theory. Okay, you can see here on screen. So what we are building is a system where you ask the question, okay, and the system search your document. Okay, you ask the question and system search your document and pick the most relevant one. Okay, and give that to the AI, so the AI answer based on your data instead of guessing. So that's what RAG is, and we are doing it without the vectors. So you can see here this diagram, user ask the question, okay, and then user ask the question and then system search your document, okay, and pick the most relevant ones, okay, and give that to the AI, okay, and give that to the AI, and the AI answer based on your data instead of guessing. Okay, so first you need to ask question and search, it will search in the documents and pick the best answer and give it to the AI, and AI generate the answer. So that's it guys, this is called the RAG pipeline. But guys, you can see we have full form of RAG: retrieve, augmentation, generation. It has three pipeline. First is retrieval, second is augmentation, and third is generation. Okay, and here you can see we are not going to use any vector, so that's why it is called the vectorless RAG. Okay. So guys, you can see here we have 1 2 3 4 5 files. Okay, so I'm going to teach you vectorless underscore rag.py file. Sorry, vectorless underscore rag dot ipynv file. Okay, so I have vectorless rag inside this file. Okay, then we will learn about these files, okay, one by one. So our first file is vectorless underscore rag dot ipynv. Okay, I'm going to close this. So here you can see we are going to learn complete vectorless rag. Okay, so rag without, we are going to learn rag without embedding, without vector database, and without API cost. Okay, so you can see here, okay, so you can see here this is our document. I'm going to explain everything one by one. So today I'm going to explain a concept called the vectorless RAG. RAG stands for retrieval, augmentation, and generation. I hope you already knew about this. Okay, so it is a technique used to help the large language model like GPT or Cloudy answer the question using your own data instead of only relying on what they are trained on. Okay, so what problem does RAG solve? Okay, so you can see here what problem does RAG solve. Large language model are trained on public internet data. Okay, this means they don't know your personal document. This means they don't know your personal document, don't know your company data, don't know your PDF or private data. So if you ask them something specific to your own data, they may guess or hallucinate. Okay, so what problem does React solve? Like Cloudy, GPT, or any other models, they don't have they have only public internet data. They don't know nothing about your data, your company data, and your private data. Okay, so with the help of RAG, okay, you can see here, with the help of RAG we can fix this, searching your document for relevant content. Okay, so how RAG fix this? First is search your document to fix the relevant information. Okay, and then it add that information into the prompt as a context. Okay, inject the content into the LLM prompt as a context, and LLM answer based your data, that is not hallucinate. Okay, I'm going to remove those, this is the error, guys. Okay, so finally the language model used as context to generate the answer. Accurate answer. So first the search, first it will search your document to the find relevant information. Okay, and then it add the information to into the prompt as a context. Okay, it add that information into the prompt as a context, and finally the language model use the context to generate the accurate answer. So that's why we use this here. Okay, searching your document and add that information into the prompt as a context, and LLM answer your question without hallucinate. Okay, so traditional RAG also we can understand what is traditional sorry, this is our traditional RAG. So we can understand the difference between traditional RAG and vectorless RAG. Okay, so you can see here in traditional RAG, retrieval. Okay, in traditional RAG they use retrieval and also use cosine similarity on embedding. Okay, I hope you already knew about this when you when you all, yeah, I hope you already learned about RAG. Okay, so retrieval here in traditional RAG means simple RAG. We have cosine similarity on embeddings. We have different similarity search, like semantic search, keyword searching, hybrid search. Okay, there. So we are, we will, we used cosine similarity or embedding inside the RAG. But in vectorless RAG, we are going to use embedding 25 keywords scoring. Okay, so here we only use 25 keyword scoring. Okay, and here you can see embedding model require OpenAI, etc. We use here different model like Almin large. Okay, sentence transform, OpenAI embedding. So we have different kind of model for embedding, so we can use this kind of model for RAG. And without vector I mean without vec sorry without vector RAG, here vectorless RAG, we don't need to use any of embedding model. Okay, and here it required the vector database. RAG required the vector database like Pinecone, Chroma, Files, Baby8. Okay, there is a lots of embedding model, but in vectorless DB we don't need any vector database. Okay, and cost, uh, embedding API cost. Okay, and vectorless RAG, it's a zero cost because we are not going to use any what any paid API or any paid vector DB. Okay, and setup, its RAG setup is heavy and vectorless setup is minimum because we don't need to require any paid setup here. Okay, semantic search, it required the semantic search, and here it is also required the partial semantic search. Okay, exact keyword matching can miss, but it is giving answer excellent. Okay, and best for large corpus semantic query, and this is best for small medium offline keyword queries. Okay, this is used for large corpus and semantic query, and this is used for vectorless dv, small medium offline keyword query. Okay, so traditional RAG use embedding for semantic search, need vector dv, and more powerful but more complex and expensive. In vectorless RAG, use BM25, keyword scoring, no embedding required, no vector dv required. Okay, and simple, fast, and cost free. I hope you got it. So, so here in traditional RAG, I mean we use embedding vector. Here we don't need to use anything like this. Okay, and when to use vectorless RAG. This one, when to use vectorless RAG. So this approach work best when you have a small to medium sized database. Okay, you have small to medium sized data sets. Okay, not database, you have a small to medium sized data set, then you will use vectorless RAG. Okay, you want a simple offline system. Okay, if you want simple offline system, then you can also use vectorless RAG. Okay, and you can also about the exact keyword matching. This is also giving the answer based on exact keyword matching. Okay, you want zero API cost setup, then it will good for you vectorless RAG. Okay, so I hope you got it, difference between traditional RAG and vectorless RAG. Now we are going to understand what this diagram. Okay, so now let's understand how vectorless RAG actually work step by step. Okay, so think of like a pipeline, data flow through the different stages before we get the final answer. Okay, so here data flow through the different stages before we get the final answer. Okay, so here you can see your document mean we start with your documents. Okay, uh, I mean the document can be notes. Okay, here document can be notes, PDF file, articles, or any custom knowledge base. This is the raw data that the system will use. Okay, now we have second step, BM25 index. Okay, so it's just a math on word frequency, no neural network. Okay, so BM25 क्या क्या होता है? So BM25 is a simple, BM25 is a simple mathematical method. Okay, that work on a word frequency. This one, BM25 is simple mathematic method that work on a word frequency. This one. Okay, so it does not use neural network, it does not use neural network or embedding. It only check how often a word appears. Okay, how often word appears and how important that word is access documents. Okay, so it is going to check only two main things. First is how often a word appears. Okay, and second one is how important that word is across the document. Okay, how important that word is across the document, how important that word is across the document. And first is how often word appear. So it is going to check two main things, how often word appears, and second is how important that word. Somebody is calling me, sorry guys. So it is going to check two things, how often a word appears and how important that word is across the document. Okay, and we have user query. So then a user ask the question. Okay, here user ask the question, for example, what is BM25? This is the question. This query is processed. Okay, this query is processed and broke into a what? Broke into a keywords. Okay, so query break and break down into a keywords here. Okay, so after this we have BM25 score each document. So it's mean what? BF25 score. Okay, so now BM25 compare the query with document. Okay, so BM25 compare the query with the document. Okay, each document get a score based on how relevant it is, so the query. Each document get the score based on how relevant it is to the query. So higher score means more relevant. Okay, so it is just going to calculate the score based on the relevant query. Okay, so BM25 compare the query with the every document. It is going to compare the query, this query with every document, and which one, I mean, if some query has the highest score, then it will give you the relevant document. Okay, higher score means more relevant document. Okay, and here after this we have top k selections. Okay, top k most relevant document. So after scoring all documents, we select the top k. After scoring, after scoring all the documents, we select the top k documents. These are the most relevant piece of information for the query. Okay, top k most relevant documents. So after scoring all the documents, we select the top k documents. These are the most relevant piece of the information for the query. Okay, and then we use this build prompt. Okay, build prompt means prompt building. Okay, answer using these document, prompt building. Okay, so you can see here, now we take these top document. Okay, from here I got the top documents. Okay, so here now we take these top document and build the prompt here. Okay, so basically we can say here are some relevant document, use only this information to answer the question, so LLM get the real context instead of guessing. Okay, so we are giving here prompt and say that here are some relevant document, use only this information to answer the question, so the LLM get the real context instead of guessing here. Okay, now we have LLM response. Seventh is LLM response. Finally the prompt goes to the language model here. Finally prompt goes to here, this prompt goes to here in a LLM model. Okay, or we can say language model like GPT, Cloudy, any of model. Okay, so this model read the context and generate the final answer here. Okay, so guys, I hope you will get, I mean you got it. Okay, so BM25 here, BM25 is the core of the system. It stands for best match 25, B for best, M for match, and 25. And it is the same ranking algorithm used in a system like Elasticsearch, Apache, Apache Solr, and many real world search engines. Okay, so it has been used and tested since the 1990, so it's very reliable. So so that's how vector rag work, simple, fast, and completely without embedding or vector database. Okay, and you can also understand this diagram also. This is also same diagram. Document, then we use BM25, and then query, and then re-rank, and then top document prompt, and give the prompt inside the LLM, and it will generate the answer, guys. So you can also use this diagram also. Okay, so it stands for best match 25, I mean BM25 best match 25. Okay, so guys, now we are going to understand code. So first, after this, I hope you got this diagram. Okay, and now you can see here knowledge base, your private document. Okay, this is the data your rag will search through. In a real project, this document could be PDF, chunk, database, rag, Wikipedia pages, anything. Okay, so I'm going to use this document. Okay, here in future it may be you have your own personal PDF text file. Okay, and your own data, but I'm going to use this document. Okay, this is my personal, suppose we don't have this data in internet. Okay, so that's why I'm going to write here. So this is our variable name, that is document. Inside this I have one list, inside the list I have multiple dictionaries. Okay, and in dictionary I have ID number. Okay, title, that is Python basic, and content equals to, I have some content inside this. Okay, and we have another ID to another title is machine learning overview, and content definition of machine learning something. Okay, again we have rag system and content and its id 3. Again we have another document, id number 4, title and content. ID number 5, title and content. ID number 6, title and content. So guys, we have these documents. Okay, 1, 2, 3, 4, 5, 6. Okay, so I'm going to print here, load it, and length of document. Okay, so I mean length is length of this document, that is 7. Okay, so length of doc, because we have 7 IDs, and you can see here it's 7 documents. Okay, so here we are going to print, I mean load it, length of document into the embedding base. Okay, so you can, that is going to check here, loaded document, that is 7. Okay, document into the knowledge base. Okay, so this is the come from with this line. Okay, I'm going to use loop here for doc in a document. So I'm going to use loop inside this document to get the one, I mean each document one by one. Okay, so print document id. Okay, so you can see here 1, 2, 3, 4, 5, 6, 7, these are the documents id and title. Okay, so I get python basic, machine learning, rag, vm25 algorithm. So these are the titles of documents, guys. Okay, you can see here we have titles. Okay, so this is our personal data I'm going to use in this code. Okay, after this we will learn the bmw25 math. Okay, so guys, we can understand bm25 now. Okay, so first I mean we are going to understand the core of this system, that is bm25 scoring algorithm, this one. Okay, so bm25 is basically way to figure out how relevant a document is to the user query. Like if you have any documents, then it will check that this document is relevant or not with the user query. Okay, so bm25 is basically a way to figure out how relevant a document is to a user query. Okay, it used two main ideas. First is tf, term frequency. Okay, tf means term frequency. This simply means how many times does a word appear in a document. Okay, it will check how many time does a word appear in a document. You can see here, if the query word vm25 appear 5 times in a document, the document is probably about 25 vm25. Okay, so I mean it is only check like how many time document, sorry, how many time does a word appear in a documents. Okay, but raw count is not enough. 100 word doc with vm25 5 times is a less focus than the 20 words doc with it 5 times. So we normalize by documents length. Okay guys, you just need to focus on how many times does a word appear inside the documents. Okay, for example, if we have word v25, this one, if we I mean if the word v25 appear 5 times. Okay, if vm25, sorry, if the word vm25 appear 5 times in a documents, okay, then the document is probably about v25. Okay, and you can see here, but there is a problem. What is the problem? A long document might contain the word 5 times. Okay, and the short document might contain it 5 times. But but the short only is actually more focused. Okay, so we fix this by normalizing with documents length. A long document might contain the word 5 times, and short document might also contain the 5 times. Okay, what the short one is actually more focused, so we fix this by normalizing with the document length. Okay, like if you have any document, and in this document we have v25 and 5 time. Okay, but if you have less, I mean short document, or there is also you have v25 and 5 time, but short document is actually more focused. Okay, okay, so we are going to normalize it with the help of document length. Okay, so second term. Okay, so second one we have inverse document frequency. This one, inverse inverse document frequency. Okay, so second is inverse document frequency, or idf. Okay, so this tell us this tell us how important a word is score all the document. Okay, this tell us how important a word is score all the documents. Okay, you can see here the word that appears in a every document. It is error. Okay, so you can see here the word the appear in every document. It is useless for ranking. The word BM25 appear in one document. It is very useful. So here, if a word like the, okay, if word like the appear everywhere, it is not useful. Okay, it means the word appear in document everywhere, but it is useful. Sorry, useless, not useful. It is useless. The word that appear in every document, it is useless for ranking. Okay, the word appear like the everywhere, it is useless. Okay, and not useful. But if a word like BM25 appear in one in a only a few document, it become very important. Okay, if you see there, if we have word that is BM25, okay, appear in any document, that means it is useful. Okay, but if word like BMW appear in only a few document, it become a very important. Okay, so IDF, this one, give the higher weight to the rare but meaningful word. Okay, like it is not meaning for the, so that's why it is giving importance to the BM25. Okay, so this is our final formula. Okay, so IDF formula, IDF term basically calculate by using this formula how rare this word across the all the documents. More rare equals to more important. Okay, so you can see here we are going to use this formula. IDF term equals to log bracket, again bracket n minus df. N is the total number of document and df means number of the documents containing the term plus 0.5 and divided by df is equals to number of the document containing the term. Okay, so this is the number of document plus 0.5 plus 1. So we are going to use this formula, guys. If you know what NLP, we already use this kind of things, IDF, TED. Okay, so turn frequency we already use inside the NLP. Okay, so this is the formula I'm going to use, and this is the final formula. Okay, so BM25 contain both TF and IDF into one formula. Okay, so score query document equals to sum for each term in a query. Okay, sum for each term in a query means summation over each term in a query. So don't worry about memorizing it, just understand the idea for each word in the query. Okay, so we are going to use this formula for each word in the query. Okay, each word in the query. So here we are going to check how often appear in a document TF. Okay, so this form in IDF term equals to TF. Sorry, IDF term into TF into K1 plus 1. Okay, so we are going to check how often it appear in a document TF. Okay, we check how rare it is across the document IDF. Okay, and then we combine both to get a final score. This one and this one, and then TF. TF tell us how much this document talk about the word. IDF. IDF means tell us how important that word is. How important that word is. Okay. And BM25 combine both to rank the document properly. Okay, so these are two important settings. We are going to use these parameters. K1 equals to 1.5. Okay, K1 is there. So control term saturation, how much repeated word matters. Okay, and b equals to 0.75, control the document length, this one b. Okay, and 1.0 fully normalization. Okay, and zero point 0.0 no normalization, let's implement from scratch, no library need. Okay guys, so there is no need to revise or remember this formula. Okay, just think we are going to use this formula idf inside this. Okay, so no need to revise these, I mean remember these kind of things. Okay, so tf tell us how much this document talk about the bird. Tf tell how much document tell about the word. Okay, and idf tell us how much important that word is. Okay, and bm25 combine both the rank document properly. It is going to combine the formula of both of them. Okay, so we are going to use this formula here, so no need to remember about this thing. Okay, just remember one thing. tf means it tell us how much this document talk about the word. Okay, and idf means tell us how important the word is. Okay, now we are going to understand this mathematics. So here we are going to understand BMW, sorry, BM25 guys. I am already confusing with BMW or BM. Okay, so now we are going to do code for math, sorry, code for BM25. Okay, so you can see here I already import math, import RE and import collection. Okay, so you can see here this math is used for logarithmic. Okay, used for logarithmic in idf calculation. Okay, because we already have log inside this, so we can use this math formula, I mean this math here. Okay, import RE, this is used for text cleaning and tokenizing. This is used for text cleaning. This is used for text cleaning. Second line RE. RE means we are going to use regex or use for text cleaning and tokenization using regex. Okay, and here you can see I'm going to import from collection counter. So this is used to count the word frequency in documents. Okay, and this is the function. This function convert text into a clean word token. This is used to convert text into a clean word, or that is called the tokens. Okay, and this line you can see here, convert, this line is going to convert text into a lowercase by using this text convert into a lowercase. That's why I use lower method to convert text into a lowercase and extract only words from A to Z. And here we are going to extract word from A to Z. Okay, and remove the punctuations, number and symbol. Okay, with the help of this we are going to remove punctuation, numbers and symbols. Okay, so here this function convert text into a word or clean word or token. Okay, and this line are used for convert the text into a text into a lowercase and extract the word from A to Z. Okay, and remove the punctuation, number and symbol. And here you can see we have another class, that is BM25. Okay, this class code search engine logic. Okay, so you can see here this is the constructor defined in it. Inside this we have self, documents, k equals to 1.5, b equals to 0.7. Okay, okay, I already explained k1 equals to control term saturation, how much repeated word matter. Okay, and b equals to 0.75 means control the document's length normalization. Okay, so these are the parameters name. Here I am going to pass in a constructor. Okay, and here you can see b equals to control the document length. Where is b? This one. V is going to control the document's length normalization, and k1 equals to k1s. Okay, control the term frequency impact. Okay, and with the help of this it is going to store the what document. Okay, store original documents. Guys, these are the variable document k1 and v. I already use these. Okay, k1 b Okay, and document. Now we have self dot token, self dot docs underscore token. So with the help of this, convert all the document into a token list. Okay, with the help of this self dot underscore document underscore tokens, we are going to convert all the tokens. Okay, convert all the tokens into a list. Okay, so you can see here we have titles and content, then we are going to use this here. Okay, so first combine the all documents. Okay, so here you can see self dot document underscore token equals to tokenize the title and content for the 4D in a document. So here we are going to combine all document into a token list. Combine you can see here document title plus document content. Okay, and then we have loop 4D in a document. So here in this what is the meaning of this line? Convert all document into a token list, and we combine title. You can see here we are going to combine title and content, so both are searchable. We are going to combine title and content here. Okay, okay, that both can searchable. Okay, so convert all the document in a list. So we are going to convert all the document in a list, and here we are going to combine title and content. Okay, and here in this line total number of the document, self dot n means length of document. Okay, self underscore self dot token self dot docs underscore token, so it means total number of document. Okay, and here with the help of this we are going to calculate average document length. Okay, self dot average length. So we are going to calculate average document length with the help of this one. Okay, so you can see here average document length used for normalization. Here you can see sum of length of d for d in a self dot document and divided by self n. Okay, so here guys, this is the simple formula of average sum of length of all documents. Okay, and divided by number of document. Okay, length of document. So here this is the formula for calculating the average length. Okay, and here you can see we have this self dot df variable. Okay, so document frequency dictionary, this is the df means document dictionary, sorry, document frequency. Okay, so document frequency dictionary, this is the empty dictionary for document frequency. So here you can see I use for loop. Okay, so loop through each document for documents in self dot doc tokens. Okay, so we are going to use loop for each document for term in a set doc. Okay, it means set doc ensure each word is counted only once per document. Each word is going to count here. We are going to count each word. Okay, each word count only once per document for term in a set docs. Each word is counted only per document. Okay, and here self dot df term. Okay, self dot df term equals to this line. This lines means what? So for term in a set documents, for term in a set documents, I already explained this. So ensure each word is counted only one per document. Okay, and we have self dot term. Here we are going to count each word per document. Okay, by using this line self dot df dot get term 0 plus 1. This is the frequency. This is the frequency formula. Okay, so this is count the document. Okay, so ensure each word is counted only once per document. Here we are going to count the what word per documents with the help of this guys. Okay, now we have this idf. So what is the meaning of idf? So inverse document frequency. It measures the how important a word is across all the document. Okay, so this means this means what? It measure the how important a word is across all the document. Okay, so here we pass self and term. Okay, this term. So here you can see this means this line. Where is it? Where is it? This line. Array. Again, it is like going top and down. Okay, so this line df equals to self dot df dot get ton comma 0. How many document contain this ton? It means how many document contain the term. Okay, and it will return this bm25 IDF. Here we are going to return math.log, and this is the formula for IDF. So here we can put b bm25. Okay, so this is formula for bm25 IDF formula. Okay, bm25 IDF formula, log scaling. Here we are going to use this formula, guys. Okay, we are put the values of ndf. Okay, so here with the help of these things, now we are going to use this function. Why we use this function? So this function calculate bm25 score for one document. Okay, so should I mention here in comments? This function calculate bm25 score for one document. Okay, so this function calculate bm25 score for one document per query, one document given a query. Okay, so here you can see, here I pass self and query and I. Okay, so here q underscore token equals to tokenize. Here I pass the query, convert the query into token. So here it is going to convert query to the token. And here what we have, doc equals to self dot doc underscore token. Okay, selected document. So here it is going to select the select document. Okay, select document I. Okay, means we are going to select the document here. Tf means here tf equals to counter documents. Count the, it means count the word frequency. Count the word frequency in the document. And length of document we can calculate by using this. Okay, and score equals to 0, my means final score. This is a final score for this document. Okay, and here I'm going to use loop through each word in a query. So here we are going to use loop through each query. Okay, so loop through each word in a query. So I'm going to use for t in a p underscore tokens here. If not, here you can see frequency. Okay, so it means frequency equals to 2f tf dot get. Inside this I pass t and comma 0. How many times word appear in a documents? It is tell us how many times the query term appear in the document. Okay, and if not frequency, okay, if word not in document, if word not in document, okay, then skip. Okay, so with the help of continue we can skip. And now we have idf equals to self dot idf. So it means importance of word. Importance of word. Okay guys, and you can see here we have another line, BM25 formula. So this is the formula. God, it is like boring, but it's okay, no problem. But it is important, okay? So this is the BF25 formula. Score equals to, I'm going to use score equals to score plus IDF into frequency into self dot k1 plus 1, close the bracket and divided by this. So guys, this is the formula I already show you there. Okay, we are going to use this formula. Okay, and return the score here. So return final relevance score here. Okay, after matching, this is the function retrieve the, this is the function retrieve the top matching document. Okay, okay, this function retrieve the top matching document. Here I pass the query and top k equals to 3 means top 3 documents. Okay, and here score equals to empty. So here you can see calculate the score for each document. Okay, it is going to calculate the score for each document. Here I pass I and self dot query, and here query and I for I in the range of self of n means document. Okay, so here we are going to use loop for find out the score of every document based on the query. Okay, calculate the score for each document for I in the range of like this. Okay, and here scores equals to, sorry, scores dot sort, this line right here as what I mentioned, calculate score for each document, and here I can mention sort by score descending order. Okay, sort document by the score, sort document by score. Okay, and here it is going to return what, return the top k result with title plus score. So here I mention in comments, return top k result with title and score. Okay, so it will return the title, okay, top title of top k result and with the score, and here it will also return the score. Okay, okay, and I use for loop for I as in a score, and it will give you top k documents. Okay, so here we are going to use return for the top k result with title plus score. Okay, I use title and score, and it will give us top k documents. Okay, then we are going to run this. Here you can see bm, this is our bm section, or we can say run section. This is a run section. So bm25 equals to bm25 documents. Create a bm25 model using the document. So here create bm25 instance with our document. Okay, and here this is basic print statement. Okay, bm25 ready and document equals to bm25 n. Okay, this is for documents. And average length of document we can calculate like this: vm25 average length, and we are going to pass 2. It is giving us for 2 document. Okay, and print the result. I use loop for I in vm25 retrieve machine learning algorithm, print the r. So it is giving us answer by using this query and vm25 dot retriever. So I have finished, guys, this one. I use this class vm25. So here I'm going to run this. K1 is not defined. I did mistake. VM25 document. Mm-mm. Actually, I even didn't touch this code. I don't know why I got error. Let me check this one. Tokenization is correct. And this one, K1 equals to K1. This is the K1, not S. Okay, guys. Self dot K1 equals to K1 because it is saying K1 S not defined. Okay, so you can see here VM25 ready, and document is 7 VM25.n. It is, we have 7 document and average length is this one. Okay, and result, I'm going to ask what is the machine learning. It is giving us machine learning overview. Okay, and it is use title from this document machine learning overview. Score, its score is 6.836. Okay, so you can see here we have this document machine learn. Inside the document what we have, this one. Okay, so this is the documents I'm going to use here. I mean, I'm not going to use BM25 is going to use here. So machine learning overview, and score is 6.83. So this is our first document it is giving us. Okay, and you can see Python basic, it has 0 score, and this is also 0 score. So the answer is, topic is this. Okay, we are getting answer from this document. Okay, so guys, this one VM25. Okay, so this code, this code, sorry, this one, this code build up BM25 search engine. Okay, first it convert document into a token. Okay, you can see here, first it is going to convert document into a token. Okay, first this convert document into a token, then calculate, then it is going to calculate what, calculate word frequency. Okay, IDF, inverse document frequency. Okay, it calculate the word frequency and document frequency. Okay, it is going to calculate word frequency and document frequency, guys. Okay, okay, and after this, when a query come, it score each document with the help of this. It is going to score each document with the help of this function. Okay, using IT, inverse frequency and inverse document frequency. Okay, you can see here it is going to use inverse document frequency and inverse frequency. Okay, so when a query comes, it score each document using IF and IDF. Okay, and finally return the most relevant document. Okay, and finally return the most relevant document with the help of retrieval, and we got our output here. Okay, so this is simple technique. This is, guys, not simple, it is like complex and confusing. No problem, you will get it after learning or writing code by your own. You will definitely get it. Okay, okay, so now you can see here, we will understand this. BM25 score each document. Okay, so here let's pick one query and see the raw score for every document. This show exactly why BM25 rank documents the way it does. Okay, so this is the query, this one. This is the query, okay, that search given by the user. Okay, so this is the search query. This is the search query given by the user. Okay, this is the query given by the user. Okay, or you can say search query given by the user, and the query is BM25 ranking algorithm for search. Okay, this is the question, and query token equals to tokenized query, this one. So this means it convert the query into clean tokens. This one is going to create the query into the clean tokens. Okay, what is the tokens, guys? It is going to convert in tokens like this. Let me show you here. If we have query convert into a token, for example, we have this, we have this question. Okay, so I'm going to convert this into a token. So how can we convert? Like this, inside the list we are going to put this one. Okay, guys, so query token equals to tokenize the query, and this is the query like this: BM25, okay, in double quotes, comma, ranking also separate in comma, with comma, okay, and algorithm inside double quotes I have algorithm, and again we separate with comma, and I use this for here in double quotes, and again we have search this keyword. Okay, so it means we are going to convert tokens of this query. Okay, these are the tokens, guys. Okay, and here it is going to print the query with the help of this, and this is going to print the query tokens. Okay, so these are the, this is the query, and this is the query tokens in output. Okay, and it is going to print, this is for empty, and it is going to print, this is for empty line. Okay, and it is going to print rank of document that is less than 5. Okay, and score greater than 1 2, and document title. So it is giving us this line, what, print the original query. This is used for print the original query, and this is the print the tokenized version of the query. Okay, and this is just a blank line for better output readability. And this one is used print, this one used for what, print the table header for rank the result. Okay, like this we have I mean rank is less than 5. Okay, so this is the rank of document from 0 to less than 5, so 0, okay, and here we have scores greater than 12. So these are the scores, score from greater than 12. So 1 minute, and this is used for title, the this is just simple. Okay, document title, so this is the title, guys, and this is the scores. Okay, and this is the rank. So this is going to search the table, I mean print the table header for ranking result. Okay, so this is going to print the table based on ranking result. Okay, and this is for like display the result like this. Okay, this is just simple line. Okay, so here we can store all these scores. Okay, store documents index and its score. We are going to store all the score here. Okay, all the score here, and we are going to use this line, all score, this one. I'm going to use this function, guys. Okay, BM25 ऑब्जेक्ट यूज करना है. ओके, रिट्रीवर नहीं है यहाँ. ठीक है, आई ऑलरेडी हैव दिस नोट्स. ओके, सो हियर आई एम गोइंग टू यूज लूप for IDX in range. I'm going to apply loop and find out the ID inside this BM25. N means documents. Okay, S equals to BM25 score. So this is give us score. Query's score based on its ID. Okay, all score append ID and score. Okay, so it is giving us inside the all score. I'm going to append ID, number of document, and their scores here. Okay, so this is loop for calculating the all score for each document based on ID and their document. Okay, and their S means scores. Okay, so print the final rank result. Okay, and here all scores dot sort, so it is going to use lambda for sorting the result. Okay, so sorting the all scores here, and I use this one, this one. Okay, this line give us highest score, most relevant score. Okay, and this line store the document index and its score. Okay, and this line print the final rank result. Okay, so that's why I use enumerate here. For rank, idx means id, s means score, enumerate all the scores, and one I passed here one for one score. Okay, and here I use bar. So it's this meaning of this lines. Optionally visualize convert score into a var of has. Okay, this one has. So we are going to print this kind of has, this one has. Okay, so based on rank. Okay, like its rank is this much. Okay, so it is going to print this. Okay, so rank of id as is enumerate all the score and I pass one. So it in bar I print this has integer s means score into 3. It is going to multiply score with 3, score with 3 here, and visualize the bar option here. Okay, if we have a score equals to 4, then it is going to multiply by 3, so it is giving us var has score. Bara has here 3, 3, 6, 9 and 12. Okay, 12 score. Okay, and print the rank. So this is our rank and scores and documents id title. Okay, okay, and this is the bar. So guys, this is the var, document title, and scores and rank. Okay, in the last it is going to print everything. So guys, print the rank number here, print the rank number, score here, and document title and visual var. So this is the var, document title, scores and rank. Okay, so this code, this whole code, this code take a user query and convert into a token. Here it is going to take user query, convert into a tokens. Okay, and convert into a tokens, then it compare this query with every document using bm25 scoring. Okay, here it is going to use query and its token. Okay, to compare here. Okay, then it compare query with each document using bm25 scores. Okay, it is going to check each query, compare each query with bm25 scores. Guys, this is the scores. Okay, okay, and each document get relevance score here. Okay, relevant score here. And after all, after this, all document sorted here, all document sorted based on rank, title, scores. Okay, so all document are sorted based on their scores. So finally the most relevant document are printed with their rank order. Okay guys, so this is the more relevant document. Okay, so the query is bm25 ranking algorithm for SRAG. So it is giving us 4 score of this, and document title is this bm25 algorithm. So you can see here we have bm25 inside this document, this one bm25 algorithm, and this is giving us this. Okay, so its score is more than other. Okay, the score is 4.3160. Vector database its score is 2. Okay, so these are score with less than this. Okay, so we can consider this one. Okay, so you can see here step number 4, BM25 breakdown. Okay, so BM25 basically check how important a word is in the document and across all the document. It give high score if the word is rare globally but frequent in that document. Okay, so here you can see we are going to use this class BM25. Okay, so I'm going to create this class VM25. Okay, here we have constructor. Okay, inside this I pass self documents and this one k1 equals to 1.5 and b equals to 0.75. These are the parameter, guys. These are the parameters. Okay, and here what I'm going to do, here this is the variable name for document, store the original document title plus content, this one. So this is going to store the original document, and self dot km is what it is going to control how much term frequency matter with the help of this. Okay, and here self dot b equals to b control document length normalization, long document versus short document. Okay, this is used for normalize the length of documents. And this one self dot token sorry document tokens, so it will combine title and content. Okay, it is going to combine title and content and then split into a word. Okay, so we are going to pick document d in a documents and then combine the title and content. Okay, here we combine title and content and then split into a words. Okay, and with the help of this line, what is the meaning of this line? Total number of the document in the data set. Okay, so self dot n equals to length of self dot doc underscore token. It's the means total number of the document in the data set. Okay, and here self dot average underscore length. So here we are going to calculate what average document length used to normalize the long versus short average document length. So here we are going to calculate average document length with the help of this sum of length d for d in a self dot document divided by self dot n. Okay, and this is the self dot df. So guys, this line is used for document frequency dictionary. Store how many document contain each word. Okay, in dictionary. And this line is used for loop through each document. Okay, loop, I'm going to apply loop for each document in each document. Okay, and you can see here this line for term in a set document. Term in a set document means use set doc, this one set doc, so we can count each word only once per document. Okay, and this line self dot df term is equals to self dot df dot get term comma 0 plus 1. It means increase the document count for this term. Okay, for example we have bm25 appear in a 3 docs. Okay, so it will give us doc bm23 equals to 3 here. Okay, it is going to count the frequency inside the document. Okay, and here frequency or word inside the document. Okay, and here you can see I have another function, sorry, another function, that is idf. Okay, so I'm going to use this for inverse document frequency. So here get the document frequency of the term. Okay, with the help of this we will get the document frequency. Okay, how many document content it. Okay, self dot df dot get term 0, and after this we have scores this one. So first you can see here, this one, it is going to return what? So idf importance of a word. Okay, idf will give us importance of the word, and rare word equals to high score, and common word equals to low score. Okay, so it is going to return with the help of this formula. And now we are going to use the scores. Okay, so here with the help of this line, convert the query into the token words. Okay, and document equals to self dot document underscore token. Okay, underscore token, and inside this I have doc underscore id. This line means get the document at given index. Okay, tf equals to counter doc. It will count the frequency of each word in a document. And this one, length of the current document, this one. And here score is equals to 0. Score equals to 0. And here I'm going to use loop for term in a frequency, sorry, term in a query in a query underscore tokens. Okay, so this loop throw each word in query. And here we have frequency equals to tf dot get term comma 0. So how many time query word appear in a document, and if not frequency, then it will skip. With the help of this, now you can see here get idf. Okay, so importance of the word in a whole data set. Okay, and this one is used for what? This line, bm24 numerator boost term frequency. With the help of this, then we have another variable dn equals to frequency plus self dot k1. So it's meaning of this line, why we use this line. So bm24 denominator controls saturation plus normalization here. With the help of this formula, I'm going to use this formula, guys. Okay, and then we have score, final score. So final contribution of this term to document score. Score plus equals to idf into number divided by dn, and it will return the score. Okay, and here we have another function, that is retrieve. Inside this I have self, query, and top k3 score equals to infinity list, sorry, empty list. So here I'm going to use loop. So compute the score for each document. Okay, so compute the score for each document. Score dot append. Here I pass I and score, and inside this I have query and index. So compute the score for each document here with the help of this line. And here we are going to sort documents by the score, highest first. Okay, and here we are going to store the result, final top result, top k underscore documents. So here you can see I use loop for I s in scores, this one, and from 0 to top k. So it means take top k documents and get the original documents. Doc equals to self dot documents. Okay, and here inside this result I'm going to append title, content, and score, and it will return the result. Okay, so return the structure result like this, title, content, score, and it will return the best matching document here, guys. Okay, guys, so this is used for matching the scores or searching the document. Okay, okay, guys, now we are going to build our small RAG pipeline. Okay, full RAG pipeline. So this is our RAG pipeline, step number 5. So now that we understand how BM25 retrieve the relevant document. Okay, guys, so here we use BM25 to retrieve the relevant document here. Initially we did tokenization and use the class b25. Okay, and we are going to retrieve here, we we were retrieve the relevant document, and the next step it is going to connect it everything, okay, with RAG. Okay, so this is for the VM25 score each document. This is used for calculating the score, and this is why we are going to match the frequency here and for search, and here we are going to create the full RAG pipeline. Okay, so now we connect everything with VM25 retriever. Okay, and with prompt and with LLM, and LLM generate the answer. Okay guys, query VM25 retriever will prompt LLM generate the answer here. Okay, so you can see here in this part we will take the retriever document, okay, and convert them into a structure prompt and send them to the LLM to generate the final answer. So basically we are going from search context answer. So here you can see I use build underscore prompt. Okay, so here I pass the query and retrieval document. Okay, output should be in string and context underscore part. So you can see here this is used for store the context. Okay, so after this function create the final prompt that we send to the LLM. Okay, and this is the list will store the formatted document, and here loop throw with the help of this line I'm going to use loop. So loop throw retrieve document, loop throw the retrieve document. So for I comma documents and enumerate retrieve document, and here I pass the one. So here loop throw retrieve documents and number them 1 2 3 4 5 like this, so many, so on. Okay, so here with the help of this line we are going to use loop, and loop throw retrieve document and number them 1 2 3. Okay, and content equals to doc dot get content. Okay, so content safely get the content here with the help of this line. Okay, and prevent crash if missing. So context underscore part dot append, we are going to append documents. Okay, and title and score and content, it is giving us content here. Okay, and context equals to this line. Okay, so format each document with the title, score and content. Here we are going to format each document with title, score and content. Okay, and here this line combine all the document into a one big context block. Okay, so here with the help of join we are going to combine, and it will return your helpful assistant use only to the given document. Okay, so this is the prompt inside this return. Okay, we are going to use these things: return helpful assistant use only given document, and here it is going to use context as a input, sorry, as a context as a document, and question as a query. Okay, and here we have another function vector rag. Okay, vectorless rag. So here we are going to use vectorless rag. Okay guys, so here we are going to use vectorless rag. Inside this I'm passing query VM25 top k integer equals to 3 and use LLM and bool equals to false. Guys, I'm just going to pass VM25 from here, and then I pass top k and query and LLM use equals to bool equals to false. So this is the full vectorless RAG pipeline. VM25 is retrieval, prompt building, and Grom LLM option. So this is for display the result. Okay, and this step are used for retrieve the document VM25 dot retrieve query and top k documents. Okay. Okay, And here I'm going to use loop in all retrieve documents, and it will print the score and title of the document here. Okay, so which document were selected? Okay, so get the top relevant document using BM25. Okay, so with the help of this we will get top result. Okay, and so which document were selected. Now we are going to use build prompt, this one. So prompt equals to build underscore prompt. Here I pass query and here I pass retriever underscore document. Print. Here I'm going to print. This is for like display. Okay, it is going to print from 0 to 400 prompt. So first part of the prompt for debugging, this one. Okay, step 3, it is giving us answer here. Okay, in step 3 answer. So here I use, if you use LLM answer, call the LLM prompts. Okay, otherwise if retrieve document top k document is equals to 0, sorry, top retrieval 0 document, so it is giving us the answer with title and context and split with the dot, and else no relevant answer found out. Okay, so here it is going to call, here it is going to call the real LLM grok, otherwise here it use the demo mode no API, and here pick the west document. With the help of this it is going to pick west document, because we have index 0, at index 0 what we have west document. Okay, it will print the west document or pick the west document. Okay, and here we have answer no relevant document find out. Okay, okay, so if document is not find out, so it is giving answer, this answer. Okay, and print the answer, and here it is going to print the answer. Okay, and here it is going to return query, retrieve documents, and prompt and answer. Okay, so this is the final answer. Here it is going to print. So guys, this is our first RAG pipeline. Retrieve, build the documents. Okay, so this function connect everything. First we retrieve document using BM25, and then we convert those document into a structure prompt. Okay, finally we either send that prompt to an LLM or return a demo answer. Okay, I hope you got it. First function connect everything, I mean this function connect everything. First we retrieve the document, okay, with the help of BM25, and then we use BM25, then we convert those document into a structure prompt. Okay, and then finally send that to an LLM or return the demo answer here. So guys, here you can see we are going to move here, test the RAG demo mode. Okay, no API key needed. Run different query and see which document get retrieved and why. Okay, so you can see here, this is the function retrieve. Here I pass query and top k. Okay, top k means top 2, top 3 document that is relevant to our query. Okay, score equals to empty. So this function find the most relevant document for the query, and this will store document index and score pair. Okay, so that's why I create score equals to empty list, and here I'm going to use loop here. So this is the loop through all documents. Okay, so for I in the range of self dot n means document, so here I am going to use loop through the all document, and here s equals to self dot score, and here I'm going to pass query and I. So it means what? Calculate the BM25 the score for each document, and here I use score dot append, and inside this I pass the I and S. So it will give us a score document Okay, score document index plus its score. Okay, and this one score is going to sort. Okay, sort the document by the score. Okay, sort the document by using the score. So here is score dot sort. Okay, so I'm going to sort the document by using score. Okay, and here result equals to empty list, final list of the top documents. Okay, final list of the top documents. And here I'm going to use loop to take only take only top k documents here. Okay, and doc equals to self dot documents. So take only top documents. Okay, doc equals to self dot documents I, get the original document using index. Okay, and in result dot append title, content, and score. Document title, document content, and relevance score. Okay, this one is relevance score. S means score. Okay, and return the top matching document. Okay, now we are going to connect our grok API. Okay, here set your API key belong to the get real answer from grok instead of demo mode. Okay, so here I am going to import os used to access the environment variable, and .env. From .env I am going to import load underscore .env. Okay, so this one is used to load the variable from the .env file that I already have this env file. Okay, and here I have this variable name inside this env file. Okay, this file, and you can see here grok API key, this one os dot get env grok API key. So it will fetch the API key from the environment variable, and this is the function call LLM. So call grok LLM and return the response here. I pass the prompt inside, call the grok LLM and return the response here. Okay, if not grok API key find out, then it will generate the answer no grok API key is found out in a env file. Okay, and here iterate is giving like this, from grok import the grok. Okay, grok import the grok client library here, and client equals to grok API key. So create the client using the API key, and response equals to client dot chat dot completion, create the model. So I'm going to use this model. Okay, and message equals to role user role, and content equals to frame, or maximum token is 512. Okay, so this is the specify the LLM model, and this will use to send the prompt as a user message. And this one maximum token means limited response length. Okay, and it is going to return response dot choice zero index message dot content. It's mean extract and return the generated answer. Okay, so here you can see after this we have accept import error. Okay, so if grok library not installed, then it will give us error pip install grok accept as e. Okay, so create another error. So this is also giving us another error, and it is going to print grok LLM ready, and here it is going to print API key loaded as if grok API key, otherwise else no. Okay guys, so this is our answer. So this function I mean this function connect our RAG to a real LLM. It load the API key, send the prompt to the model, and return the generated answer. If the API key missing or something fails, it handle with the error. Okay, so LLM doesn't know anything by itself here. It only answer based on the retrieve context we provide. Okay, so that's why we use this. Now you can see we have this line of code. So here you can see we have vectorless underscore rag. Inside this we have query, Query means user question what we want to answer, okay? And BM25 equals to BM25 pass the BM25 retriever we built earlier, okay? And top k equals to 3 means retrieve top 3 most relevant document. Use LLM equals to use LLM use real LLM like Grok instead of demo mode, okay? So here we are using model. So here we are calling the full RAG pipeline here. We pass the user query, the BM25 retriever and specify how many document we want. Then we enter the LLM so it generate a real answer instead of a demo response. This will retrieve the top document, build a prompt and send it to the LLM and return the final answer. Okay guys, so you can, what is the query? This is the query and it is going to match the query score 1 from vector database. Sorry, score 4.0. It is giving us top 3 documents. Okay, I already passed here top 3 documents. It is giving answer. This is the question and answer this question by using these 3 top document. Vector database, BM25 algorithm. Okay, this is the top first, top second and top third. Okay, and prompt, you can see you are helpful. This is the prompt guys. Okay, and we have 3 documents name, vector database, BM25 algorithm and machine learning. Okay, and this is the question. Okay, so in knowledge base I already create knowledge base. We have answer of this. Where is it? This is our knowledge base guys. Okay, so first is vector database and second is BM25 and third is machine learning. This one, so you can find out a score like this. So guys, this is our answer and you can see here, this is the query. What is the BM25? How it is different from the vector search? So it is going to retrieve title and vector database search score and its score is 4.6. Okay, that is higher than the other. So we have 3 topics here. Okay, and this is the prompt and this is the answer. Based on the retrieve provide the document. So it is giving answer here. This is the answer. Okay, now we are going to add your own documents. Okay, so replace or add to the document list with your own data. Okay, so this is the error guys, this is nothing. I'm going to remove this. Okay, there is it, no retraining, no embedding, no vector db migration. Okay, so we are going to add our own data. So there is no training, no embedding, no vector db migration. So here I pass my document equals to documents id equals to 8 and here title and content. Again I'm going to pass our document id number, title and content. In content we have our content and we are going to rebuild our BM25 model with new doc. Okay, BM25 new, BM25 my documents. I pass this document here. Okay, this one and print the new knowledge base. So BM25 underscore new dot n means document. So this is giving us a document. Okay, this is the query, test query. So here result equals to BM25 new retrieve the fast API sync python API. So top 3 result I want from this. Okay, so this is the question, fast API async python API and this is the query, fast API async python API. From doc in result it is going search in a search the document in the result and give the score and title. Okay, so you can see here I got the query and score of this and title of this query. Okay, again we have this one, another we have is this one. Okay, so these are the document with high score of this query. Okay, so we can also compare here vector database. Okay, so retrieval method we can use in vector RAG, cosine similarity or embedding. Okay, and here in vector RAG, vectorless RAG, we are going to use BM25 and TF IDF keyword to scoring. An embedding model require text embedding, 3 sentence transform, OpenAI embedding, etc. No need of embedding here in vectorless RAG, and vector database require in RAG. There is no need of vector RAG here in vectorless RAG. There is no need of vector DB. Setup complexity is high, is low, and cost of this vector rag is high because we use API here, and its cost is low. Okay, we don't use any API and paid service here, so that's why its cost is low. Semantic search, yes, find the similar meaning even with a different word. Only if the word is met, it is going to find the it is going to use semantic search. Okay, exact match can miss, it is giving us exact match, that is excellent. Best for large and semantic query, and this is for small corpus and keyword query offline it is use. Okay, so here this is our another demo, 20 VM25 retrieval demo. Three different queries, see which document get retrieved and how they are ranked. Okay, so we have three document inside this. Okay, BM search ranking algorithm, Python programming language, neural network, deep searching. Okay, so it is going to print, this is the for displaying purpose. Okay guys, live 25 V25 retrieval demo, and here we are going to loop, or use loop. Okay, inside the document query, and it is going to print the query, and here with the help of B25 retriever I got the query. I got the top k results. Okay, if result for rank in a rank and documents in enumerate result, and here 1 2 3 whatever we have number of documents. Okay, print the rank and score, print the rank, score and document title, else no matching document, find out. So you can see here BM25 searching the ranking, so we got rank 1, rank 2, rank 3, and this is the score, AV score. Okay, and this is the title, this one is title and title. Another query, Python programming language, we have rank 1, rank 2, rank 3 score, these are the scores, and this is the title again similar. Okay, so guys, this is basically math walkthrough from the scratch. So you can see here I'm going to import math, I'm going to import RE for regex, and here I'm going to import counter. Okay, so here a query equals to this one BM25 ranking algorithm, and document I pass this document. Okay, and here it is going to display the result. Also here it is going to display the query, and here it is giving us text of document from 0 to 60. Okay, now it is going to tokenize the query with the help of this query tokens, refill all. Okay, A to Z, and query should be lower. So we will we will create the token. Okay, and if we have something else other thing, then it will replace. Okay, and token doc underscore token, so here I use find all, and we are going to use A to Z, and doc test equals to lower. So query is also in lowercase, convert, I'm going to convert, and document underscore text also I'm going to convert into lowercase. Return the copy of string, here it is going to return the copy of string converted to the lowercase. And here TF map, so this is going to create the matching. Okay, matching frequency TF map, and these are the BM25 parameter I already explained, number of document, DF term, document length, average length, and K1 and B1. Okay, and these are for print the core and print statement. Okay, for query underscore token, and it is also print the TF, IDF, and BM25 scores. Okay, and here we have total equals to 0. So in term in a query tokens. Okay, so here I'm going to use, guys, this is the formula here, I'm going to use formula in term in a query tokens. Okay, so we are going to apply here formula, this one is formula, TF equals to TF underscore mob get the term and 0. Okay, so this is going to find out the frequency, term frequency, and this is the formula of IDF. So we are going to calculate IDF and IF. So if IF equals to TF equals to 0, not IF, it's a TF. Okay, again we are going to calculate number, and this is also formula, and this is the scores, right? This is the formula, and else it is going to return the score equals to 0. So total score it is going to print here. Okay, so term, so this is for term, this is the for TF, IDF, and IDF should be like this, and score should be 12.45, and term should be less than 0.15. Okay, so it is going to print total and higher total score, more relevant document. Okay, so you can see here, this is the query and this is the document. BMWT is BM25 is a ranking function used in information retrieval. And here token equals to ranking and algorithm. It is going to print term, ranking and algorithm, IATF 1 and 0, IDF this one and this one, and this is the score, and total equals to 2.1075 score ka total guys. Higher total score equals to more relevant document, this one. Okay, so this is going to calculate the total score that is greater than 0.4. Okay, so summary, vectorless RAG in 3 steps. Store, put your document in a plain Python list. Search VM25 score each document using the keyword waste math, no embedding. So we will not use any kind of embedding, just use this kind of math. This is boring guys. Okay, and answer equals to top k retrieved document are passed into the LLM as a context. Okay, so here I pass top k element into the LLM where I use LLM. Maybe here this one I use this LLM here. Okay, and I pass context as a prompt here. Prompt as a context, whatever. And when to use vectorless RAG, small to medium knowledge base where we have less than 100k documents. No embedding API budget, no API user offline, we can do it offline. Okay, edge device deployment, exact keyword matching is important, legal, medical, code search. You want it a simple and fully debugging system. So here you can see when to upgrade to vector RAG. Queries like find document about this sadness, semantic meaning, not keyword. Multilingual search requirement, very large data set, billions of document, meaning matter more than the exact word matching. Okay, so if you want like this, I mean this kind of requirement, then you can use vector RAG. Or if you have this kind of requirement, then you can use vectorless RAG. Or if you have this kind of requirement, then you can use vector RAG. So popular library I use rank underscore BM25 pure Python BM25 implementation, and Boost full text search engine in Python, SQLite build BM25 based on search in SQLite, zero dependency. Elasticsearch production skill search engine with advanced query. So here you can also use minimal working example using rank BM25. So we need to install this. Okay, so here I'm going to import from rank underscore BM25 import this. Okay, BM25 okay API, and here I use corpus document. I'm going to split content with splitting the content from the documents. Okay, and here we are going to pass corpus this one. And here what is the query is this BM25 ranking, so it is giving us a score BM25 dot get a score, and corrected it is, split. Okay, so this is simple example guys. I'm not going to run this. Okay, because it said that it is going to set that install this. I'm not going to install this because I haven't created virtual environment. Okay, you can check with this also. Okay, I'm going to save this file. Hello guys, welcome back to my channel. Today we are going to understand what page indexing chat with the help of RAG, or we can say vectorless RAG. So most document question answering the system today rely on vector database and similarity search that work until it doesn't. context get messy, retrieval becomes shallow, and long document turn into a guessing game. So newer approach move away from pure similarity search toward the reasoning based retrieval. So I'm giving you one example is page index chat. This use a vectorless RAG framework designed to handle the long document more reliably and transparently. So in this video I will show you how to use page index chat API and SDK to upload a document and process it and ask the question over it without worrying about the context limit or information loss. Okay, as it is actually answering the question like a semi-organized human instead of a confused auto complete engine. Okay guys, so now we can see here we are going to understand page indexing with the help of vectorless RAG. Okay, so what is the problem in traditional RAG? Traditional RAG work like a breakdown document into a chunk and convert into an embedding and retrieve the top match chunks. Okay, but the problem is chunking break content context. Okay, chunking breaks the context and similarity is not always accurate. It retrieve based on a matching and not understanding. Okay, so sometimes the answer is in the document but the system just miss it. Okay, so you can see here this is the diagram for traditional vector array. Okay, so you can see here you can see here. Okay, so a document here you can see we have one document. Okay, so let's start with the traditional approach used in a most RAG system. Okay, today a document here you can see we have document and document is split into a small chunks here. Here you can see in small chunks. Each chunk is converted into a embedding here. Okay, and stored inside the vector database. Okay, when user ask the question. Okay, user ask the question here. Okay, user query and also did the embedding of user query. Okay, when user ask the question here. Okay, user ask the question here, query is also convert into a embedding here. Okay, and then the system retrieve the most similar chunk using the similarity search or quotient similarity search with the help of this. Okay, okay, so finally these retrieved chunk are passed into a, here we got a retrieve chunk top k chunks. Okay, and these retrieved chunk pass to the LLM and LLM generate the answer here. Okay guys, so this is the traditional RAG. Okay, so the issue is that similarity is not the same as understanding. The system retrieve what looks similar, not necessary what is actually relevant. Okay, so it is not going to understand that is necessarily that it is relevant or not sometime. Okay, so that's why we are using page index. Okay, that will overcome the limitation of vectorless RAG. So it is going to it is going to improve this is going to improve page index limitation of RAG. Okay, so that's why we use vectorless RAG. Okay, so here you can see this is the diagram for vectorless RAG. Okay, this is the diagram number 2 for vectorless RAG, and here I use page index. Okay, so now look at the page index chat. Okay, so here you can see instead of relying on vector similarity search, if we have document and we use processing page index. Okay, so you can see instead of relying on vector similarity search, it processes the document in most structured way and use the reasoning to locate the relevant information. Okay, so here if I am going to process these document here, okay, with the help of index processing, it will give us what the reasoning of the document in a more structured way. Okay, instead of relying one vector similarity search, it processes the document okay in more structured way and reasoning and use the reasoning to locate the relevant information. Okay, so when a question is asked by the user here. Okay, so we got the reasoning of document. We have document and process the document, and we will get here reasoning of document in a structured way. After here you can see after user ask the question here. Okay, it doesn't just fetch the similar text. Okay, it doesn't fetch similar text. It navigate it doesn't fetch just similar text. It navigates through the document and identify identify where the actual answer exists or not. So it is, if you are asking the question here, so it is use its intelligence and navigate answer that is correct or not. Okay, and then okay, so the system then provide an answer along with supporting page reference here. Okay, relevant evidence and page reference here, and it will generate the final answer here. Okay guys, so this suits the system from finding the similar text to understanding where the answer live in that documents. Okay, so vector rag retrieval similarity vector rag retrieval similarity page index try to retrieve the meaning here. Okay, so what, so the shift the system from finding the similarity text to understanding where the answer live in the document. This will understand where the answer live in the document with the help of this. Okay, and vector rag retrieves the similarity. Vector rag retrieve the similarity. Page index try to retrieve the meanings. Okay, page index try to retrieve the meaning, and vector rag try to retrieve the similarity. Okay, so that is why vector rag approach like page index are become interesting nowadays. They reduce the dependency on embedding and focus more on structure reasoning over the documents. Okay guys, I hope you got it. So guys, you can see here this notebook. Okay, we are here in page index chat. I'm going to maximize this. File name is page index underscore chat underscore quick start dot pyNV file. Okay, so here you can see document QA with page index chat API. Okay, so this is the page index vectorless RAG approach. Okay, so instead of splitting document into a chunk and using vector similarity set, it organize the document into a structure representation like a tree. Okay, like a tree. So when you can see here when a user asks the question. Okay, when user asks the question, the system doesn't randomly search for the similarity test. It use LLM reasoning here. Okay, here it is going to use LLM reasoning to navigate through this structure step by step. Okay, so the model identify relevant part of the document, follow the logical path, and the and extract the exact information needed. Okay, so finally it return the answer based on the document structure, not just surface level similarity. Okay, so you can see here document means structure document. Okay, so document is structure into a tree, not a chunk. Okay, so we are going to use documents and we need to structure these document in tree. Okay, not in chunks. Okay, after this you can see here query goes into the reasoning LLM reasoning engine. Okay, query goes into the reasoning engine here. Okay, and system navigate document logically here, and you can see here user ask the question and then output here it generate the output with the help of query and context, grounded context. Okay, so this is like diagram. We need to have document, then we need to do tree. We need to split into a, we need to send here. Okay, query goes into the here in LLM reasoning from here. Okay, so here we use tree. Okay, so instead of chunking I'm going to use tree. Okay, so when a user asks the question, system doesn't randomly search similarity, it use the LLM reasoning. Okay, so that's why it is giving us giving an answer by using the query. Okay, so we need to give here document. Okay, document structure in a tree, structure into a tree like this, not into a chunk. Then we pass this tree and document here inside the LLM reasoning. User ask the question and generate the response. Okay, so this approach replaces brute force similarity search with the structure reasoning over the document. Instead of asking what looks similar here, okay, it asks where does the answer actually live in documents. Okay, so here we are going to use this Okay, so this notebook demonstrates simple minimum example of doing document analysis with the page index chat AI API on the recent release NVIDIA 10 question report. Okay, so we are going to install this page index because we are going to use page index here. So we are going to use this for page index, and I already use this API, guys. I already show you multiple times. You can create your own API key from here. Okay, and the URL of this dash.pageindex.ai hyphen API keys. Okay, so you can find here your own page index API key. Okay, so here you can see from page index I'm going to import page index client. Okay, so guys, you can see here we set up our page index here. Okay, so I import page index. From page index I import page index client. Okay, so import the page index SDK client class here. Okay, why? This give you access to the page index API. So here I need to mention this give you this gives you this gives you access to page index API features. Okay, so this gives you access page index API features including document, submission, query, and many more. Okay, and this give you access to page index API features like uploading document and asking the questions. Okay, and we have this line, get your page index API key from this URL. I already show you. So this is my API key. You also put your API key here, page index API key. Okay, so with the help of this we can access our query. Okay, so here we are going to store our API key as a variable page index underscore API underscore key. Okay, so why we use this here? The API key is required to authenticate your request. Without this, page index will reject your call. Okay, it need to know it's really you. Okay, and I use this page client. Okay, page underscore client. Here I pass the page index client, and here this API. Here API key equals to page index API key. Okay, so create a page client object using your API key. Okay, so I mention here create a client object using your API key. Okay, so we just use this. Okay, so create a client object using your API key which you can use to interact with the page index API. Okay, and after this, why we are going to use this? So this is your main connection to the page index service. Okay, this is the main connection to the page index service. You use this object pi underscore client, this one. Okay, to upload the document. You use this to upload the document, check the document status, and ask the question over the document. So here I mention you use this client, okay, to submit the document, check their status, and query them once they are ready. Okay, and here okay, so now I have finished this. So this code initialize the page index SDK so we can interact with the API. First we import the page index class, this one. Okay, which is the main interface for working with the service. Okay, and then we provide our API key which authenticate our request here. Okay, and finally we create client object, this one. This object is what we use to upload the document and run the query. against them. Okay, so I use these kind of things. API key means your ID card entered the system. It is like ID card. Okay, and import means bringing the tool into your kitchen or something. Okay, for example, client object means here, for example, client object means remote control for the whole service. Okay, so I use this thing here. Now you can see here I upload the document here. Okay, so first I'm import OS and request here. You can see here OS and request. So OS used to handle the file path, this one, file path and folder in a system independent way, and request means to download the PDF from the internet. Okay, so we have this document. I'm going to search this URL here. Okay guys, so this is also NVIDIA papers. Okay, based on, you can see here NVIDIA paper, NVIDIA Corporation financial statement. Okay, so where you can find the more information about the NVIDIA transition report. Okay, so you can see here this is document. I'm going to ask the question from this document. Okay guys, I just use this NVIDIA paper. Okay, and here this one. Okay, so this is the document. Okay, we want to analyze, and in this case it is a real NVIDIA 10Q financial report in PDF format. Okay, this is the 10Q financial report in PDF format. Okay, so this is the NVIDIA 10Q financial report in a PDF format. Okay, and after this we have this path PDF underscore path os dot path join. It means what? So we create a local file path where the PDF will be saved. Okay, so here this is the local path that we can save our PDF inside this. Okay, inside this data folder, and it is use this last name, this one. That's why I pass the -1 here. Okay, and here this one is used for what? Okay, so you can see here I use PDF dot split. So extract the file name from the URL. Okay, this one used for extract the file name from the URL. Okay, so instead of saving a messy URL, we store it at a clean file in a data folder. Okay guys, in previous video I already store here data file here inside data, and here this one os.mac dir. So this line means this create the underscore dot data folder. Okay, this create the dot hyphen data folder if doesn't already exist. Okay, if folder is not there, then it is going to create the folder. Okay, this line, and then exit. Okay, true means don't crash if the folder is already there. Basically make sure storage exists before saving the anything. Okay, so like if folder doesn't exist there, then it will create, otherwise no problem. Okay, in this path directory. Okay, and here you can see response equals to response that get PDF URL. So what is the meaning of this line? Okay, so we send a get request to the download this PDF. Okay, so here we are going to send the get request. Response equals to response dot get request PDF URL. Okay, so we send the request to download the PDF from the internet. Okay, this PDF from the internet, and with open, you can see here with open what is the meaning of this line? With open PDF, I pass here PDF path and WB. So it means what? We send, here what I'm going to do, we open a local file. We open the local file here. Okay, like this, if this file is saved here, after downloading it is going to save here, then we are going to open this file. Okay, open the file in a write binary mode. That's why I use WB, write binary mode. F means file. Okay, and then Then we have this line write response dot content, this one response dot content. So here we write the downloaded PDF content into the file, okay, and print PDF URL. So guys, this is the PDF URL, and document submitted, this is the document. Okay, so here you can see, just here we are going to confirm message, so we know the download succeed or not. Okay, because silence in code usually means something broken. Okay, so here you can see, after this we have this line. So now we upload the PDF to the page index here. Okay, we upload PDF into the page index. So document equals to pi underscore client submit document to the page index. Okay, so we just now we upload the PDF to the page index here. Okay, and here I give the PDF path and document ID. Okay, so page index process the document. Page index process the document here. Okay, okay, and it return the document ID. Okay, so you can see here, this is the document ID, document submitted document ID. So page index return a document ID which we use to reference it later. Okay, so this I mean in this code, first we download a PDF. Okay, first we download the PDF document from the internet, and then we need to save, okay, and we need to save locally, and then API need a file path, not a URL. Okay, and after this we upload the document to the page index here. Okay, and which process and index if it for the query, and finally we get a document ID which act like a handle to interact with this document later. So this is the page ID. Okay, we will use later. So you can see here, after this upload document, we are here, check the processing status. Okay, so you can see here I use this pprint. Okay, I import pprint from pprint. Okay, so with the help of this, it can display API response in a readable format. Okay, instead of dumping messy JSON on the screen like a joystick debug log. Okay, and here you can see, this is the another variable doc underscore information. So here I call the page index with the help of pi client. Okay, so call the page index API to fetch the information about the uploaded document. So here with the help of this, we are going to fetch the information about the uploaded document. This return the metadata like status, number of page, and processing status. Okay, so that's why I print here this. Okay, and here you can see I use like this, it is going to give us this kind of metadata. Okay, and here you can see if document underscore information status equals to complete. So this mean was, it is going to check if the document has finished processing. This one is going to check if document has finished the process. Okay, so on page index server, if the document has finished the processing on page index servers, okay, because the large PDF are not instantly ready, so they need time for indexing and analysis. Okay, so that's why we use if document information status is complete or not, because large document take a lots of time, so it is giving you answer that it is in progressing, and it is ready to give you answer. Okay, then it is going to print document ready like this, and number of the pages. You can see here it is going to print document ready for giving the answer, and here it is going to print page numbers. Okay, here, and else status equals to processing. It means what? If status equals to processing, if process here you can see what is the meaning of, if the document is still being processed. Okay, it is going to print document is still processing, please wait and check again. Okay, so if the document is still being processed, this is the common for large files, so we don't try to query it too early. Okay, so this is giving us status, like our document is incompleted or not, or it is in processing. Okay, so here finally with the help of this it is going to print. So you can see here it is giving us metadata, created date, this is the date. Okay, and here this is the description. Okay, and here id of document, name of document, page number 48, and status complete. Okay, okay, now we can ask the question because it is ready to ask the question, and question is about this document. Okay, now we can ask the question about this document. Okay, so 1 minute. Okay, so we call here get underscore document, this one, so to check the processing status. Okay, so we are going to use this here because we want to check the status, processing status. If the status is complete, it means you can ask the question. Okay, and otherwise you need to wait for. Okay, wait for that is ready or not. Okay, if it is still processing, we just wait because the system is still building its internal representation of the documents. Okay, and after this we have this ask the question about this document. Okay, so here you can see I define the one query, what is the revenue, also show me which page I can find out. Okay, so we define the user query, it is question, and we want to ask the question about the document. Okay, ask about the document, and here you can see I use chunk. So here we call the page index with the help of this CI client. Okay, so we call the page index chat completion. You can see chat completion API. So we call the page index chat completion API to interact with the uploaded document here. Okay, this is not a normal LLM call. It's a document grounded QA. Okay, here, and this is like this one you can see here. Here we are going to pass what we pass the conversation message here. Okay, conversation message in a OpenAI style format. Okay, and user, like who is going to ask the question. Okay, so this is the user, and in context I pass the query. Okay, so even though it a single question, is it still expect the message list. Okay, and I use document id, doc underscore id equals to doc underscore id. I already have document id. Where is this? This is our document id, this one. Okay, so here you can see we use document id. Okay, where is this document id? Okay, so this tell API which document we are querying. Without document underscore id, it wouldn't know which PDF to search in. Okay, and stream equals to true means response will come in a parts chunk, not at once. Okay, response come in a chunks or part, not at once. Okay, so this allow the real time output like ChatGPT this allow real time output like ChatGPT typing effect. Okay, and here I print each chunk is a small piece of the final answer. Each chunk is a small piece of the final answer. We print it immediately to response appear gradually. Okay, so I use and here, that is not taking any space or any extra line. Okay, and I use plus here. Okay, and this is the answer. Okay, I will help to find out the revenue from NVIDIA 10Q report. Okay, let me first check the document structure. So this is the answer from the document revenue detail. Okay, and you can see here key highlights. Okay, so this is our answer, guys. So first you need to define here one question. This is the question, and then you basically ask the question, answer creation. Okay, and here we use this client. Okay, page index. So guys, I hope you got it. So this is our simple code for document QA with page index chat API. Okay, just you need to upload the document here. Okay, and page index API, you need to upload page index API here, and you need to access API key with the help of page index. Okay, and after this you need to upload document, then you can check that it is upload properly or not. or you can save this document inside your local folder, that is data. Okay, the kind of this folder data, inside this you get this file after running this. Okay, and then we can check here download status, that it is downloaded or not. Okay, and we created here document id. Then check the response if this document is uploaded completely or still in process here. Okay, if it is complete, then we can ask the question, otherwise we will wait for complete it. Okay, and then we can ask the question. Guys, this is simple process. Okay, here we don't need to do any kind of chunking, we don't need to use any kind of vector database. Okay, we can process long documentation here. So hello guys, welcome back to my YouTube channel. Today I'm going to explain what vectorless agentic RAG. Okay, so most RAG systems today depend on a vector database and chunking and embedding. But what if you could retrieve the information just by asking, like GPT does? Okay, so in this video, I will show you new approach called the agentic retrieval using page index chat. Okay, where the model decide what to retrieve instead of relying on a similarity search. That's it. Okay guys, so you can see here problem with traditional RAG. Traditional RAG work like this. Break the document into a chunk, convert chunk into a embedding, and retrieve top matching chunks. Okay, but this has a problem. Chunking breaks the context. Okay, similarity search is not always the accurate. It retrieve based on matching, not understanding. Okay, so sometime answer is in the document but the system just miss it. Okay, in traditional RAG you can see here, we just follow the step. User ask the question, then we use embedding model for embedding. Okay, we also did the query embedding here. Okay, and then we need to go here in vector database and find out the top k chunks. Okay, and LLM generate the answer here. Here we are going to use, I mean, semantic search here or cosine similarity search to find the similar chunks. Okay, then LLM generate the answer. This is the simple step of traditional RAG. But you can see here agentic retrieval with page index. Okay, so here suppose user ask this question, what are the evolution method in this paper? Okay, so here instead of searching sorry, so here we are going to use query user query. So this is the question the user ask this one, what are the evolution method in this paper? Okay, and then LLM reasoning. So here this is the brain of the system. The LLM like GPT understand the question and decide what to look for and where it might exist in the document. It is not doing keyword matching, it actually thinking here. Okay, then we have third step, document full context. Okay, so instead of searching small chunks, the model has access to the entire document. Okay, there is no need of chunking, no vector search, and no filtering beforehand. Okay, it can explore document like a human would. So it is like, let me check the methodology section. Okay, maybe result section has this. Okay, so it is going to check everywhere. Okay, and here you can see relevant content extraction. So now the model pick only the useful part from the document, extract the specific paragraph, ignore the irrelevant content, and it can even return the structure output like JSON. Okay, so this is the retrieval step. What does using reasoning here? Okay, here and here finally answer. So this is the, I mean, finally the model uses the extract the content to generate the close answer, more accurate based on actual content and not guessing based. Okay, not random guessing based. So this is the this is the system work while letting the AI think, then find out the right content and fully generate the answer instead of blindly searching using similarity. Okay, so imagine I'm giving you one example. Imagine you have book. Okay, so imagine you have book, and instead of searching random sentence, okay, you understand the question, think with the chapter has the answer and go there, and read only the part and give the answer. Okay, so that's exactly what this system is doing. So this method is smarter but also slower and more expensive compared to the traditional RAG. Okay, I think it is not expensive. Okay, we will see after practical. Okay guys, so you can see here we are going to create agentic retrieval with the help of page index. Okay, so you can see here notebook overview. Okay, so in this notebook we are going to learn with the help of this example of agentic retrieval with the page index. Okay, so here you can see how to use page index chat API and how to prompt the page index chat, how to prompt the page index chat to make it a retrieval system. Okay, so here if you don't know page index uh, API key, so you can go here in dashboard. Here you can see dash dot page index dot AI. So this is the URL of this page, and you can find out the API key with the help of this. You can click here and create your own API key by using this. Okay, click on create and make your API key. That's it, and you need to put your API key here. Okay, here. So how can we install page index SDK? So here we can install pip install hyphen q underscore underscore upgrade page index. Okay, so this is upgrade for the page index. I already installed this. Okay, you can install this, and here after this you can see here page index. I'm going to import page index client. Okay, from page index import page index client, that we can import this page index client. Okay, for access the API key of page index. Okay, so this is our page index API key, this one. Okay, and pi client equals to, this is the our client. Okay, page index client, this is the instance that we can access our page index API key like this. Okay, API key equals to page index API key here. Okay, okay, so after creating the step for page index API, we move here, upload the document. Okay, so here you can see I have I import OS and request. Okay guys, so actually we will understand why we are going to create this code. Okay, so we need to give the document. Okay, we need to give this document to the system so it can read, understand and answer the question from it. In simple term we can say this code download a PDF, this PDF, this code download a PDF, save it locally. Okay, so this is the folder name that it will save, this one, and upload to the page index. Okay, and get a document ID so we can query it later. And without this step there is nothing for the API to read. No retrieval, no answer, just disappointment. So here you can see I import OS, here OS for file handling path folder. Okay, so I'm going to import required libraries here. So first I import OS used for file handling path folder. Okay, and I also use request used to download the PDF from the internet. Okay, so that's why we are using request here. Here you can see OS and request, and you can see here this is PDF URL. Okay, if you are going to search this URL, you need to copy this URL from here, and then you need to go here and search. Okay, so this is our file, PDF file, a survey of context engineering for large language model. Okay, so this is the file from archive.org. Okay, so they provide the research file only. Okay, so this is the research based file, and topic is a survey of context engineering for large language model. Okay, so this is our URL path, PDF underscore URL. So this is the PDF URL. Okay, and we can save this here. inside this data folder. Okay, so I use this path. Okay, so here you can see this is our URL of the PDF document we want to use. In this case, it's a research paper from Archive. Okay, and this second line, create a local file path to save the PDF. Okay, this is used to save the PDF. This is the local file path, guys. You can see here we use PDF underscore URL dot split. Okay, so here we will split with it and it will give you last. Okay, so extract the file name from the URL. So it is going to extract the file, okay, with name URL. Okay, so extract the file name from the URL and save here in this folder. Okay, like this it is going to extract this last name. I use -1 and here store here in a data folder. So I have this data folder and you can see here it is giving us last name of this PDF. Okay, so I use -1 here. After this we use this os.mac directory. So create the folder. Here we create the folder data. Okay, this one, it does not already exist. Okay, so this is used for if this folder is not exist. Okay, okay, so this line is used for this. Okay, create the folder data if does not already exist. Okay, exist equals to true. Okay, exist equals to true means prevent the error if the folder is already exist. Okay, it is going to check if the folder is present there or not. Okay, if it is not, then it will create, otherwise and there is no need to create because we have exist equals to exist, okay, equals to true. Okay, okay, so in this path now we have this line, this line. Okay, response equals to request dot get PDF underscore URL. It is going to send a request to download the PDF from the internet. Okay, this is going to send the request to download the PDF from the internet. Okay, this line. So should I mention here? Send get request to download the PDF. Okay, so it is send the request to download the PDF. And we have with open, this is the another line. Okay, open the file in write the binary mode. Okay, so here I use with and open the file. This is the file path in the binary mode. Okay guys, write binary mode. Okay, and F for extend file. Okay, so this require for saving the file like PDF, not a plain text. Okay, okay, so this require for the saving file like PDF, not plain text. Okay, so after this we have this line. This line is used for what? F dot write response dot content. So this is used for saving the file content to a file, PDF content to the file. So write the here write the download content into the file. Okay, so we can also mention this is going to write the download content into the file. So here we can write like this. I'm going to remove this. Write the download content. Write the download content into the file, local file. Okay, and after this we have this print the confirmation that the file has been downloaded. Okay, so you can see here it is going to print this path because I already print this here. Okay, so here it is used for confirm that file has been downloaded. Okay, confirm the download of file. Okay, and this one doc id equals to pi underscore client dot submit document, and here I put the path underscore PDF underscore path, and here document id. So it means upload the PDF to the page index system. Okay, we are going to upload PDF to the page index system because we are going to use pi underscore client. Okay, this allow the system to process and understand the document. Okay, this allow the system to understand and process the document. Okay, so submit document, you can see here we use submit document. Submit document return the dictionary content doc id. Okay, so here should I mention? Okay, so I can mention here in comment, upload the PDF to the page index system. Okay, upload the PDF to the page index system. This allows system to process and understand the document. Allow system a few seconds to process and understand the document before querying it. Okay, and here submit underscore doc, submit understand underscore document return a document id that you can use to the query the document. Okay, so that's why we use this step. And in the end, print document submitted, so it is going to print the document id. Guys, this is the document id, this one. Okay, so print the document id. This id is important because we will use it later. Okay, okay, so I hope you got this. Okay, so with the help of this code, I mean with the help of this, we are going to download the document. Okay, we are going to download the document with the help of this and save it in locally. Save it locally. Okay, save it locally here, here. Okay, so this code, download the document. Okay, save it locally and upload it to the system so the API can read and answer the question from it. Okay, so it's look like leaving your wallet open in a crowded market and hoping people behave normally, morally, whatever. Okay, so after this, we are going to use another. Okay, after uploading document and download and give to the system. Okay, we are going to move here. After uploading document, check the processing status. Okay, so why we are doing this first? Before we can ask the question about a document, we need to know, has the document finished uploading and is it still being processed, and how many pages does it even have? Okay, so because of you start querying so too early, the system will basically shrug and say, I haven't read the document it yet, chill please. So we are going to checking document status before using it. Okay, so this is for checking the process status. Okay, so here you can see I import pp print. Okay, from p print. So this one, so here you can see why we import the p print to print here. So we import the p print to print the large. Okay, so here I can mention in comments, we import p print. Okay, we import p print to print the document information in a more readable format, or we can say we are going to import p print to print the. So here you can see I print p print, sorry, I import p print from p print. Okay, so we import p print to print the document information in a readable format, or we can say we import p print to print the large JSON dictionaries in a readable format. Okay, and here I import, sorry, I created one variable doc underscore information equals to pi underscore client. Okay, so we are asking page index here. with the help of pi client we are going to ask page index api for the current status of our uploaded document. Okay, so with the help of this we are getting current status of get the current document. Oh, no, no. So here we are going to write, we are asking page page index for here we are asking page index api with the help of page underscore client. Okay, okay, for the current status of the document, current status of current status of our uploaded document. Okay, and here it is going to print the document information. Okay, so this will return the metadata. Okay, you can see here this is going to return the metadata like this status. Okay, so you can see here this is the metadata. Number of pages, here you can see this description is none, folder id is none, this is the document id, and this is the name of document, and these are the page number, and status is processing, and document is still processing, please wait and check again. Okay, so this is giving us metadata of page. Okay, so status processing complete and processing, this is giving us like this. Okay, and after this we use conditions here. Okay, so if document underscore information status equals to completed, so here what does it mean, so here I can mention here in comments. Okay, so what is the meaning of this? If ready, we inform the user and show the total number of pages. If the document is done processing, we can start querying it. Okay, if document is uploaded, a document of status that is completed, then 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 processing done, and we start the querying it, or we will start the ask the question from this document. Okay, so it is not here you can see. After this, after completing, it is going to print document ready. Okay, this line is used for print that document is ready. Okay, so if ready, we inform the user and show the total number of pages. Okay, so here if ready, we inform. Okay, if ready, we inform the user and print the number of pages in the document. Okay, I just remove this. Okay, so if it is ready, we inform the user and print the number of the pages in the document. Okay, document is ready, and document information, it is giving us page number. Okay, so after this we have another condition, that is elif. So why we use this elif condition? So if status not finished yet, okay, if it's not finished, if it's not finished at, be handle waiting. Be handle waiting case. Okay, and then it will print the document is still processing, please wait and check. Okay guys, so I already show you, this is giving us this kind of information. Okay, and after this ask the question about this document. So you can see here we are going to move here, but here you can see we just check whether the uploaded document is ready for the question and answering or still being processed. Okay, so it is giving you answer here. Okay, after checking the process of document, after checking the status of process document, we are going to move here, ask the question about this document. Okay, so first this is the query. Query, we define query as in string that user can ask the question about this document related that we already upload. Okay, and here you can see for chunk, the question is what are the evolution method used in this paper. Okay, and here I am going to use loop. Okay, for chunk in a pi client dot chat completion. Okay, so here here you can see I'm going to use these two line. One line is iterate the loop, I mean iterate the loop here. So here why we use this line. So here we use here chat underscore completion. This is the method that allow to send the query to the document AI. Okay, or we can say function that talk to the document AI. Okay, so this one page, sorry, chat underscore completion. Okay, and here we have this chunk, for chunk. So we are streaming response piece by piece with the help of this. Okay guys, why we are going to create this? So this one. Okay, so here we are going to pass the chat completion. Okay, message and docs. Okay, so why we are going to streaming here, streaming chunk piece by piece? Because answer from the LLM can come gradually, not at once. Okay, so here after this we have message. Inside the message, I mean message equals to conversation format. Okay, like user giving answer, sorry, user ask the query here. So content equals to query and role equals to user. And here I pass the document ID. I already show you document ID. This one. This is the document ID, guys. Okay, and stream equals to true. Okay, and content equals to actual query. So here this is what the user want to know. Okay. Okay, document ID stream equals to true and role equals to in message role equals to user ask the query actual question. Okay, so why we use this? Why we are going to use this? So we are going to create this because we want to ask the question about the document and get the answer using the page index agentic retrieval system. Okay, instead of searching PDF manually, reading the page manually, extract the test manually, we just use page index chat with the help of this chat underscore completion. Okay, and with the help of this we can understand document, it will understand document and retrieve the answer and generate the, sorry, retrieve the answer with the help of this. Okay, so after this we use this print. Okay, so in this message I already passed these things. Now I already show you this document ID. Okay, so here the system answer only using this document. Okay, with the help of this document ID. Without this model would not know which file to read. Okay, so here we need to give document ID. Okay, and streaming equals to true means this enable the streaming output instead of waiting for full answer. Okay, instead of waiting for full answer we get the answer in small chunks token. Okay, so that's that this is why ChatGPT feels typing like. Okay, and after this we are going to print chunk. Okay, so in print statement you can see chunk, a small piece of generated answer. What is the chunk? So here I think you already know chunk because you already know RAG if you are learning this. Okay, chunk equals to piece, small piece of generated answer. Okay, chunk equals to small piece of generated answer. Okay, and then we are going to use end. End means don't add new line after each chunk. Okay, don't need to add new line after each chunk. Okay, flash equals to true means force immediately output. Okay, force immediate output, no buffering delay. Okay, no buffering delay, we want immediate output. So in result, answer appear smoothly. Here you can see in this result, answer appear here, okay, smoothly, like like live typing instead of waiting and and dumping the everything at once. So it is giving us answer properly in few seconds. Okay, guys, you can see I have this question: what are the evolution method used in this paper? Okay, so this is the given the answer: evolution framework and methodology. Okay, guys, so this is the query. Okay, maximum results one, document name. This is the document name, file name. Okay, and component level assessments, prompt engineering, long context processing, it is giving answer, these kind of answer. Okay, system level assessment and benchmark data sets, domain, rare context, long mamba, sliding attention suites. Okay, so this is the answer, guys. Okay, for this query with the help of page index. Here we need to, in page index, what we are going to do, we just need to provide the document ID here. Okay, now we are going to use agent retrieval with page index chat. Okay, okay, guys, so here we are going to move here. Okay, after getting the response from the document. Okay, so after this process I'm going to move here agentic retrieval with page index chat API. Okay, so we are not directly asking the model to answer the question. Instead, we are forcing it to behave like a retrieve system. Okay, so the goal is extract only relevant text from the document, not generate the final answer at. Structure output in a predictable format. It should generate the structure output in a predictable format. Why? Because it gives the control over the retrieval evidence. Okay, make system transparent, help in debugging and auditing answer, separate retrieval from the generation. So basically we are turning an LLM into a document search engine using prompt. Okay, so you can see here, this is the prompt retrieval prompt equals to, here in f string I put this prompt. Okay, this one. So guys, this is the prompt. So we are here, we create a instruction instruction prompt that tell the LLM what the role it should play. Instead of answering directly, we force it to act like a retrieval system. Okay, so here I'm just giving a retrieval prompt here. Your job is to retrieve the raw relevant content from the document based on the user query. Here I pass the user query. Okay, user query input. Okay, and return the JSON format. So I want result in a JSON format inside the dictionary, page number and content. Okay, okay, so here this is the page number where information is find out. Okay, and exact extract text from the document means content. Okay, so B initialize an empty string to store the streaming response. Here B initialize empty string to store the streaming response from the model. Okay, because response is not written all at once, but in chunks. Okay, so full underscore response, that's why we created this. Okay, we call the page index chat API with streaming. Here you can see we call the chat. Here you can see we are going to call the page index chat AI API with streaming enable. Okay, so this means response come token by token instead of waiting full output. Okay, so here you can see I use page pi underscore client and chat completion. Okay, so with the help of this we can call the page index chat API with streaming enable. So this means response come token by token instead of waiting for full output. Okay, so that's why we use this for chunk in a pi underscore client dot chat completion. Okay, and we send the prompt as a user message to the model. Here we send this prompt as a user message, okay, to the model. So I also send the context retrieval prompt, this one, okay, and role equals to user, okay, in message. And here I need to pass document id, so we attach the document id so the model know the which document to search the result or search inside, okay. And streaming equals to true means streaming mode on, response come gradually, okay. And here it is going to print chunk, okay. So it is going to print chunk immediately as it arrives, real time output, it is giving us real time output. And I use and equals to empty, that is not going to take any space or any extra lines, okay. And here I use plus equals to true, okay. And I already explained this one, okay. And here full response full underscore response is equals to full underscore response plus chunk, okay. So also store the full response for the later processing like JSON extraction, okay. So I store the full response, okay. So we can say, here we are not asking the AI answer, we are not asking the AI to answer directly here, okay. So instead we forcing it to act like a retrieval engine that extract the relevant text from the AI, okay. Then we stream the response and store it here for further response, okay. So here we are forcing it to like a retrieval engine that extract the relevant text information from the document, not AI, guys. It is you giving answer to you, it is going to use document, okay, not AI. And here you can see, this is the query, okay. So select map mcp page index get structured document maximum result equals to 1. This is the document name part 1, file path. So we have different things here. This is like metadata, okay. And here page number 35, and it is giving the content, evolution and challenges, memory evolution framework have emerged and critical component for. So this is giving answer based on page, okay. Page 36, page 37, methodology to arise when memory specific performance, okay. And this answer come from page number 41, 45, 46, 50, okay. So these are the answer, guys, okay. So guys, this is called the query equals to select, means it is going to call the tool, which tool I need to select, okay. Tool call, I mean we have three layers here. First is tool call, searching the document structure, and second is page retrieval, getting the page, okay, getting the page. This is the document name and file path, and here we have maximum result, and then we have, again we have this tool, okay guys. So it contains tool call, page retrieval, and final extract answer in the JSON, okay. And so this system work in a multiple steps, okay. First it's called the tool, this one. First it's called the tool to understand document structure, okay. And then it identify which page are relevant to the question, okay. So it is giving us maximum result, that is one, and document name this part one, okay. And identify which page are relevant to the question, okay. After this it retrieve the content from the selected page. Finally it return the structured JSON content, the page number, and extract the text, okay guys. So this is our, you can see here we have this content, okay. Page number 35, query, this is this evolution and challenge, memory evolution, okay. So this is the question, okay. Evolution and challenge, memory evolution framework. So this is the result in a JSON. You can see here we have dictionaries, this one. So it contains three things. First is tool call, okay. it is going to call the tool here, and then page retrieval. So these are the page number, and inside this we have final answer in a JSON. So this is the answer in a JSON. Okay guys, because you can see here we have this answer in a JSON. Okay, so if you have 100,000 pages book, instead of reading everything, first you check table of the content, then you pick the chapter, then you open only those pages, and then you copy the important lines. Okay, that's exactly what this system is doing. Okay, so tool call means what? Tool call means ask system what to do. Okay, and page selection means which page matter. Okay, and JSON output final extract answer. So this is an agentic retrieval pipeline where the model first select the retrieval relevant page using tool, then extract text, and finally return the structure output in a JSON format. Hmm. So you can see here, after this agentic retrieval with page index set API, I'm going to move here. Okay, JSON retrieval result, extract the JSON retrieval result. So we are installing a helper library that can safely extract JSON from the messy LLM output. Okay, so we are installing a helper library that can safely extract JSON from the messy LLM output. Okay, this is a JSON extractor. Okay, so why we need this? LLM response often include the extra text, markdown, or formatting. Okay, so normal JSON parsing fail. This library help us to cleanly extract the valid JSON. So that's why I'm going to use this one. Okay, this one JSON extractor. Should I mention here? LLM response. LLM response can sometimes include the extra text along with JSON. So we use helper function to extract the JSON from the response before parsing. Okay, so this is giving us clean output. Okay, and this is the function name extract underscore JSON. So why we are going to create this? Here I pass the content. Okay, so we define this function because we want result in a, because we want reuse JSON extraction logic. Okay, so we define this function because we want reuse JSON extraction logic multiple time here. Okay, so without rewriting the same messy parsing code again and again, we just use this. Okay, and here I'm going to import from JSON underscore extraction, import JSON extractor. Okay, so here we import the specialized utility that can identify and extract the valid JSON. It is giving us valid JSON. Okay, so even if the input text contain extra noise or formatting, it is giving us valid JSON. Okay, and here you can see I created here start underscore IDs. Okay, what is it? So guys, we look for the starting point of a JSON. Okay, here we are looking for starting point of the JSON. Find the index of the start of the JSON code block. Okay, so we are going to looking here what? Starting point of a JSON code block in a markdown format. If index underscore ID not equals to -1. Okay, if start underscore index ID not equals to 1, okay, we check if the JSON block actually exists in the response or not. Okay, we are checking here if the JSON block actually exists in the response or not. If not found, we skip this parsing method here. Okay, and you can see here we have index start index ID plus equals to 7. Adjust the index to start after the delimiter. Okay, so it means adjust the index to start after the delimiter. We move the pointer forward so we can skip this JSON text itself and start reading actual JSON content here. Okay, so you can see here, and underscore idx equals to content dot rfind. Okay, so we find the last occurrence of this, which mark the end of the JSON block. Okay, so this is giving us we find the last occurrence, okay, which marks the end of the JSON block. And JSON underscore content, here I use content, so here I pass the start IDs, IDX and end ID, and I use strip. So what is the meaning of this? So we extract only the text between the start and end markers. Okay, we only extract text between the start and end markers here, because I use start and end here. Okay, and it will return even after extraction. JSON might still be slightly malformed. Okay, and here we are going to use pprint. So this is for we import pprint to print the JSON in a readable format. Okay, and here print extract underscore JSON full response. We call our function this one, extract underscore JSON. And here we call our function on the LLM response and display the structure output clearly here. So this help us verify the retrieval system actually return. Okay guys, so here you can see, note you may need to restart the kernel. Okay, I haven't restarted, no problem, but I still got answer. Okay, so you can see here content. This is the content, normal evolution framework, hack, emergent, critical component. Okay, and this is the page number. Again, we have another content, and we have page numbers also here. So guys, after running the retrieval step, the system return the structure result like this. Okay, each result contain two things: the page number, you can see here, each result has two things: page number, where the information is find out, and the exact content, this one, exact content, I mean exact content extract from the page. Okay, you can see this is the content. So I got content and page number. So the first result come from the page number 35, this one. Okay, this one, page number 35. It talk about the evolution and challenging in the memory system for the agent, this one. Okay, and the second result come from page number 50. Okay, it explain different evolution framework and metrics used to the major memory performance in the large language model. Okay guys, so instead of just giving a direct answer, the system show where the information come from. Okay, and the exact support and the exact supporting text from the document. Okay, so this make the retrieval process more transparent and trustworthy, because we always verify the source in the original document. Okay, so you can see here we have page index. Actually I covered these things, I already covered these things. Page index is just a framework. It provides the document upload, tree building and reasoning based retrieval and chat over the document. And second thing I use in this file, pi client. Okay, so pi client is equals to your personal connection to the page index API like this. Okay, page index client, and here I need to put API keys. Okay, so in simple analogy we can say page index is like a restaurant. Okay, and page client, this one, page index client is like a waiter. Okay, and pi underscore client equals to your waiter. Okay, and you use API, so you use pi underscore client to send the document, ask the question and get the result. Okay, I also use this one, chat completion. Okay, so this one used for ask the question and get the response based on the documents. Okay guys, I use only these three things here. Okay, now I hope you got these things and this framework also. Okay guys, so I just finished these steps. Okay, these steps I just finished here. Okay, and you can see here I already mentioned this, I haven't show you this. Okay, so agentic retrieval with page index chat, yeah, API. Okay, so you can see here similarity based rag. Okay, similarity based rag based on vector DB has so big limitation in recent applications. So reasoning based or agentic retrieval has become important in the current deployment. Okay, however, unlike the classic RAG pipeline with embedding input, top K chunks return re-rank what should agentic native retrieval API looks like. Okay, so like we are going to face multiple problems in traditional RAG, like vector DB. I need to do embedding, chunking, and so many things. Okay, so here with the help of this, we don't need to use these kind of things. Okay, we can create a project with the help of page index as well in vectorless RAG. Okay, so for agentic native retrieval system, we need to ability to prompt for retrieval just as natural as you interact with GPT. Okay, so we just need to give the one prompt here as you interact with the chat GPT. Below we provide the example of how the page index chat API enable this system or prompt driven retrievals. Okay, and you can see here this is the page index chat API. So you can see here this is the description of this. Okay, so it is a AI assistant that allow you chat with multiple super long document without worrying about the limitation content or content road problem. It is based on page index as a vectorless reasoning based RAG framework which give more transparent and reliable result like a human expert. Okay, so like we have document, and then we use documentation tree and LLM reasoning, and if you are going to ask the query here, and it will generate the answer here. Okay guys, so this is the vectorless RAG with the page index. Okay, and you can see here in notebook I already show you setup of page, and I use I already show you API keys of page index. Okay, don't use my API key, you can use your own. And here how can we upload the document? Okay, so I already finished this process. I upload this archive research paper. Okay, and then status of document, that is complete or not, or in progress. Okay, and ask I use this part for ask the question about this document. Okay, and it is giving us these things. And retrieval, I also use this agentic retrieval with page index chat API. Okay guys, this is very powerful. Tomorrow, maybe yesterday, I create one video with the help of BM25. I use BM25 for searching. Okay, so this is agentic ways vectorless RAG. Okay, and here agentic RAG with page index chat. Okay, so here I pass the prompt. Okay, and here in chat completion PI client, I give the message, document ID, and stream. Okay, so it is giving answer in a page number and content, and it is giving us answer in a JSON format. Extract the JSON retrieval result here. So this is our JSON based output, guys. Okay, I already explained page index, these thing. I already finished this. Bye bye, see you in next video, guys. So hello guys, today I'm going to create vectorless RAG. Okay, so I have this file 7 underscore vectorless underscore rag dot ipynb file, this one. Okay, so instead of using embedding, vector database, and chunking, we will use LLM to reason over the document structure itself. Okay, so we have this diagram. This is our diagram for traditional RAG. Okay, this one. In traditional RAG, we have this step first. Okay, so in traditional RAG, we break the document here. We break the document. Okay, we break the document into a smaller chunks. Okay, here you can see chunk the document. Okay, then each chunk is converted into a vector, or we can say embedding. Basically a number represent of its meaning. Okay, and we are going to store these vector here inside the vector database. Okay, when query come in, we also convert the query into a vectors. Okay, and then we find the chunk with the help of similarity search, top K chunks. Okay, and LLM generate the answer here. Okay, so here is the issue. What is the issue? The system retrieve what is similar. Okay, system is retrieve what is the similar, not necessary what is correct here. Okay, for example, if I ask about financial risk, it might return a section about the market condition just because the words overlap. Okay, so the system is doing semantic matching, not understand the document structure. Okay, so you can see here we have another diagram for RAG. So this is called the vectorless RAG. Okay, so you can see here this is the diagram for vectorless. Okay, so you can see here. So you can see here query come. Okay, so here you can see here we have query, documentary, LLM region over the section, selected relevant section and fetch actual content, and LLM generate the answer. Okay, so now instead of breaking the document into a random chunk, okay, before we use chunking of document. Okay, so here we don't need to use chunking. Okay, so now instead of breaking the document into a random chunks, okay, we first convert the document into a structured tree. Okay, if we have document, then we need to convert this document into a structured tree, like a table of content, like this, guys. Okay, like if we have document, then we need to convert it's in a separate part, or we can say table of content. Like we can convert, I mean, we can create introduction separately, and financial overview, and review and expenses, and risk factor, and conclusion. So we can create every part separately. Okay, I mean, we can create the table of the content like this. Okay, so the document look like this. Okay, so here we first convert the document into a structured tree, and this is the tree, guys. Okay, like a content of table of content. Okay, now when query come in, we don't search using the vector. We don't search using the vector. Instead, we give the query and this structure to the LLM. Okay, so here you can see we don't search using the vectors. Instead, we give the query and this structure to the LLM here. Okay, and ask which section actually contain the answer. And here we give the query to the LLM and ask which section actually contain the answer. Okay, so LLM behave like a human reading a book here. Okay, it doesn't scan every paragraph randomly. It look at the index. Okay, it look at the index and find the right section. Okay, and then and then read only that part. Okay, so it LLM look at the index and find the right section and read only that part. Okay, guys, so instead of similarity based retrieval, this is the region based retrieval. Okay, this is the reasoning based retrieval. Okay, so here you can see vector rec find the similarity text here. Okay, so vector rec find the similarity text. Okay, and vectorless rec find the right section here with the help of LLM. Okay, so vector rec means match the word. In vector rec we match the words, and in vectorless rec understand the structure. Okay, first you need to give the document, and here it will create the tree structure of every document. Okay, then LLM give the region and structure, and it is all, I mean, LLM also decide which part of document have answer, and select the relevant section. Okay, and select the relevant section and fetch the actual content, and here generate the answer. LLM will generate the answer here. So in vector rag we use similarity search. Okay, find the matching word, and in vectorless rag understand the structure. Okay, so we are actually using it earlier for retrieval, not just for answering. Okay, so we are not removing the LLM here. Okay, so we are not removing the LLM. We are actually use it earlier for retrieval, not just answering. Here we use here. Okay, and now I will show you how we build this system step by step. Okay, so now we are going to install -q grok py pdf2. Okay, this is for PDF, and with the help of this we can access our API key from the env file, .env file. Okay, and here I'm going to use OS and JSON for JSON file and PyPDF for PDF file. Okay, I'm going to import Grok. That with the help of this we can use API keys and Grok models. Okay, and here I'm going to import .env. Sorry, I'm going to import load_.env from .env. Okay, that we can access our .env files API. Okay, and with the help of this we can access our API key, and this is a Grok_API_key that I have inside this env file. Okay, and here this is the our Grok API key, and this is empty string. Okay, and this is .strip. Okay, so we can use this Grok API key inside this project. Okay, and Grok model I'm going to use this one, llama 3.3-70 b billion. Okay, hyphen versatile. Okay, and client equals to I'm going to use Grok, and inside this I have API_key, means here I'm going to put Grok_API_key. Okay, so it is going to print Grok okay if Grok API, else missing, and add the Grok API to the env file. Okay, so here it is giving us yes, we have API key inside the env file. Okay, so guys, this is a simple setup for API keys and models. Okay, now we are going to load the file. Okay, so we are going to load our file. Okay, so you can see here this one, this is the path, this is the what, this is the PDF file. Okay, this is the path to the PDF file you want to process. Okay, so here you can see I have one folder, docs, this one. Inside this I have this file, annual 2023 annual report. This is our file name. Okay, so here after document I mention here file name. Okay, in PDF. Okay, and here you can replace this with any of document. Okay, like paper, report, etc. Okay, and here you can see here another variable, reader equals to pypdf2.pdf reader. Here I pass this path, pdf_path. Okay, so with the help of this, what it create a PDF reader object using the pypdf2. It create a PDF reader. Okay, it is going to create a PDF reader object using pypdf2. Okay, so here this load the document, this is going to load the document, this document. Okay, this is going to load the document so we can access its page. Okay, load the document so we can access the page of this document. Okay, and we can see here page, this is the another variable page. So it extract text from each page of the PDF. It is going to extract each page from the PDF. You can see here reader.pages. Here you can see reader, this line is reader, and this is the page. Okay, so you can see here reader.pages give a list of all pages. Okay, so this is going to extract each page, it is going to extract text from each page of the PDF. Okay, so reader.page, it gives a list of all the pages. Okay, it extract the text from all the pages and give the list of all the pages here with the help of this. Okay, and extract_text, this one pulls text from each page. Okay, so this is giving us list of all the pages. Okay, and this is used for pull the text from the pages. Okay, pull the text from the pages, and or you can see here empty string. Okay, ensure we don't get none if a page has no extraval text. Okay, so I use this loop here for I in the range of length of reader.page. Okay, so this is the document path. Okay, and here this is the document. Okay, so here we are going to use loop here. Okay, it read every page of this document and read the document and give and fetch, it will give us the list of all the document, and this will extract or pull the text from the document. Okay, and here print the, here you can see print the total number of the page loaded from the PDF. Okay, so this confirm that the document was read successfully. Okay, so I'm going to run this. This confirm document loaded successfully. PDF loaded, and we have 50 pages inside this PDF. Okay, so after this, so guys, you can see here it loaded 50 pages. Okay, we have 50 pages in this PDF. Okay, now we are going to move here in step number 4, build tree index. Okay, so why we are create this function, this build tree? So we want to convert a raw PDF, just plain text pages, okay, into a structure format like a table of content. Okay, so this tree help the LLM understand the document layout and later retrieve the correct section using the reasoning. Okay, I already show you. We need to convert content like this: first introduction, financial overview, revenue, expenses, risk factor, and conclusion. Okay, for example, we just need to convert content into a table structure. Okay, table content. So why we are creating this function? We want to convert PDF into a plain text pages. Okay, and into a structure format. Okay, and this tree help us the LLM understand the document layout and later retrieve the correct section using the reasoning. Okay, so that's why we are going to create this function. Here I pass the pages. Okay, so we only send here we only send first 15 pages, okay, to the LLM to detect the structure. Okay, so we are going to send the first 15 pages to detect the LLM structure. And here we have sample equals to empty string. So what is the meaning of this? So here you can see we only send the first 15 document to the LLM. Okay, and the reason is why we are going to send 15 documents, 15 pages to the LLM. Okay, so the reason is most document define structure, like they have they have headings and section. Most document define the structure, they have headings, they have section earlier. Okay, what save the token? So we need to save the tokens cheaper plus faster. So avoid the sending the entire document unnecessarily. Okay, so the reason is most document define a structure, like they have heading sections section early, and save the tokens cheaper plus faster, and avoid the sending the entire document unnecessary. Okay, so we have sample equals to empty. Okay, and loop, here you can see I'm going to use loop. So loop through first 15 document here. Okay, so for I and text. Okay, so I'm going to use enumerate here. It will take index and pages. Okay, it will take pages from 0 to 15. Okay, so I use loop here. So loop through first 15 documents. Okay, with the help of this line. And enumerate I pass enumerate and pages and 1. So start page numbering from 1 to human friendly. Okay, so 1 means human friendly. Okay, so start page number from 1, and 1 means human friendly. Okay, and here you can see sample. Okay, so what does it mean, sample? So for each page, okay, for each page we are going to add a clear page separator. Okay, here we are going to create a clear page separator, help LLM understand the boundary. Only take, here we only take 50, from 0 to 800 document character. Okay, we just take 0 to 800 character to we only take first 800 character to reduce the token usage. Okay, so that's why we use 0 to 800 character to reduce the token usage. Okay, so for every pages. Okay, and here we have prompt. So why we are going to create prompt for LLM? We are giving the instruction we are going to provide the instruction to it. Okay, so it will read the sample document. You are analyzer a document, you are analyzing document. Okay, and extract its section structure as the tree document first 15 pages. Okay, and sample I giving here. Okay, so here I pass the prompt. Okay, here I pass the prompt. Create a prompt for LLM. We are instructing it to and read the sample document, identify section and hierarchy, return the structure JSON format. Here you can see return the structure JSON format, no extra text. Okay, so this is the prompt I'm giving here. Okay, and it return only valid JSON array. Okay, and then send. Here you can see we have response. Okay, then send request to the Grok LLM. Here you can see we are going to send request to the Grok LLM. I pass here Grok underscore model. Okay, here I took temperature request to 0 means deterministic output, important for structure JSON. Okay, and here I pass message and user role and content. Content means whatever we have this prompt. Okay, okay, so I pass this prompt here in content equals to prompt, and this is the user role. So this is the response, this is the request I'm going to send to the LLM Grok model. Okay, and with the help of this line, extract the raw response text from the LLM. Okay, raw response from the LLM. You can see here, extract the raw response text from the LLM with the help of this response choice. Okay, 0 index, it is, and here I use this message and content dot strip. So we are going to extract the message, or we can say response text from the LLM. Okay, and after this we have clean markdown code. Okay, so here you can see raw dot start with. Okay, so sometime LLM wrap output in a markdown code. Okay, sometime LLM give you output in a markdown code block, like something JSON or markdown things like there. Okay, like this. Okay, if raw start with, this is like markdown. Okay, if you can see here, if raw dot start with, like this. Okay, so here this remove those wrappers, so JSON parsing doesn't fail. Okay, so we need to remove this. Okay, so raw equals to raw dot split. Okay, so here we are going to remove wrapper. Okay, with the help of these line. Okay, if we will check there, if we find out these kind of things, okay, this will remove, split and remove. Okay, so that's why I use this. Okay, and then convert JSON. Here you can see, then convert JSON string into the Python object like of dictionary. Okay, so here we are going to convert JSON string, JSON dot load raw dot strip. Okay, so convert JSON string into the Python object like of dictionary. Okay, convert JSON string into Python object, or we can say list of dictionary. Okay, and here inform user the, here you can see I'm going to print this. Okay, so here this is used for inform the user that tree building is starting. Okay, inform the user that tree building is starting. Okay, so tree building is starting and tree equals to build tree. I'm going to call this function. Okay, and here I'm going to print tree build and length of tree. Okay, so here print how many top level section we are found. Okay, and like main chapter in the document, like main chapter in the document. So here you can see building tree, we are going to, it takes 10 seconds and tree build one top level section. Okay, I'm going to run this. It is giving answer. Okay. So guys, here what I did. So here we take the first few pages here. Okay, we take first few pages here of the document and ask the LLM to identify its structure. Okay, because I passed the LLM here, and ask the LLM to identify its structure like heading and subheading. Okay, and then and return it as a tree. Okay, so this replace manual parsing or chunking and give us semantic map of the document. Okay, so we are converting unstructured text into a structured knowledge here. Okay, now we are going to inspect tree here. Okay, so here this function print tree. This function is used to visualize the document structure of the tree. Why we create it? The LLM build a hierarchical tree, section, subsection. Okay, but raw JSON is hard to read. Okay, so this function print it in a class human readable format like a table of content. Okay, I'm going to repeat again. This function is used to visualize the document structure tree. Why we create it? The LLM build a hierarchical tree like section, subsection, but raw JSON is hard to read. So this function print it in a clean human readable format like a table of content. Okay, so here after this I use this loop, this function. I pass here notes and indent equals to 0. Notes means note. What is the note? List of section at the current level. Okay, list of section. And intent means what? Control spacing to show the hierarchy. Okay, control space to show the hierarchy, parent versus child. Okay, and here I'm going to use loop. So print the current node section. You can see here for n in a node, so it is going to print the current node section. Okay, you can see here I use this intent. So it means add the space to the visually shift child node to the right. Okay, and here I use this line. So what is the meaning of this? Node I. Node I means this one, node ID. Unique identifier used later for retrieval. Okay, and this is the title of the section name. Okay, and here you can see p.x. Okay, and p.x means page number. This is the page number if missing. Okay, it is giving us page number. N.get, if page missing, then it will give you question mark. Okay, it will show the question mark. Okay, and here you can see I use this line, if n.get nodes. Okay, so check if the node has child section, I mean subsection. Okay, if n.get, it is going to check if it has subsection of document. Okay, and here it is going to print what? So here you can see here recursively call the same function on a child nodes. Okay, n.get node. So recursively call the same function on a child nodes. Okay, and you can see here print tree nodes and indent plus 1. Okay, so indent plus 1 means increase the spacing to show the hierarchy visually. Okay, like this here, and it is going to print header, so output is easier to understand. It is going to print the header, so output is easier to understand. Okay, and here I'm going to call this function. I pass here tree. Okay, so it will return something like this. Okay, so it is giving us report to the Congress. Okay, it is dividing content. Okay, about the Federal Reserve. Okay, and content P3, overview P7. Okay, so guys, here we create this function to convert the raw tree JSON into a readable structure, so we can visually understand how the document is organized before doing the retrieval. Okay, so this help us to see what the LLM understand about the document structure. So you can see here 001 report to the content, page number 1. This is the page number 1. Okay, I'm going to open this file. Actually, I upload this file, guys. Okay, here you can see this file, annual report truncated.pf 2023. Okay, so this is the file. Okay, so you can see here first page. This is the first page content. Okay, so it is saying what? It is saying report to the Congress P1. Okay, so this is our first page inside the report to the Congress. Okay, you can see here this one, and in second page about the 002 about the Federal Reserve. Okay, page number 5. So we can search page number 5. About the Federal Reserve. So guys, this is the page number 5. You can see here it is giving us this. In page number 5 we have this about the federal. Okay, so 001 report to Congress, page 1. So this is the top level section. This one is a top level section, basically the root of the document. And then we have this, and then we have content p.3, page content in page 3. Okay, so here in page 3 we have content. This is our content, this one. Okay, and this is the major section in the document starting on the page 7. Okay, so we have page 7. What happening here after 6? Okay, we have this 7 overview. Okay, this is the page 7 overview. So here you can see in page 7 we have overview, p7 overview. Okay, in document. So this is the major section in the document starting on the page 7. Okay, and after this we have these you can see here these 3. Okay, so this is the, I mean, you can see here indentation line. Here we have gap, here also we have gap. Okay, so this means what? These are child section. These are the child section in the inside this page. Okay, inside this topic, mandatory policy and economy development. Okay, these are the child. Okay, so these are the child section. Okay, child section meaning they belong under this section. Okay, so page 9, and inside this we can check here page number 9, 7, 8 and 9. Okay, so this is a page number 9, and in page 9 we have monetary policy and economic development, March summary and 2000 June summary. Okay, so you can see here this is the main section, and these are the subsection, March 2024 summary. Okay, so this is the summary, guys. Summary. Okay, so these are the subsection, guys. Okay, page number 9 and page number 15. So you can search page number 15. In page number 15 I have June 2023 summary. Okay, so these are the subsection of this section. Okay, and after this we have this. Okay, financial stability at 15 page. So you can search 15 page. This is our 15 page financial stability. Inside this we have. Okay, so this is our document structure in tree form. Okay, so now when I ask the question, the LLM doesn't search blindly. Okay, it look at this structure and decide which section is most likely contain the answer. Okay, so that's why we need to create document like this in a tree form. Okay, for example, I ask about the financial stability. Okay, I ask about the financial stability. So it is going to check page number what? Financial stability is there. Federal Reserve report section monetary policy and economy content overview. This one. Okay, if I'm going to ask the question financial stability, then it is going to use this section. Okay, so a human would directly go here. Okay, and now the LLM does the same thing. Okay, now LLM does the same thing. So this tree turn an unstructured PDF into a structured searchable document. Okay, so you might notice some section like content and metadata. Okay, about the Federal Reserve. Where is this? About the Federal Reserve, this one. Okay, these are the content and metadata. So content, this is the content. Okay, so these are not very useful for answering the question, but they still appear because the LLM is extracting the structure automatically. This makes you sound thoughtful and realistic. So you can see here this one, this part, guys. Page number, starting page. Okay, we have content and metadata. Okay, so this might notice some section like content, or you might notice content. These are the content and metadata. Okay, so these are not very helpful, but these are the not very helpful for answering, but still appear because the LLM extracting the structure automatically. Okay, now we are going to move here step 6, vectorless RAG pipeline. Okay, LLM read tree and pick the relevant nodes ID and fetch the pages, get actual content from the PDF. LLM answer means cited answer from the content. Okay, so you can see here vectorless RAG core pipeline. Okay, so this is the function LLM underscore tree underscore search. Here I pass the query in tree. Okay, so LLM pick which section node IDs are relevant to the query here. So why we creating this? So here, instead of vector search, we ask the LLM to look at the document structure. Okay, and decide which section likely contain the answer. Okay, so that's why we are going to create this function. And then you can see here, this is the helper function, compress. Here I pass the nodes inside this as a parameter. Okay, so this is the helper function to reduce the tree size before sending to the LLM. It is going to save the tokens. Okay, and then you can see here we are going to return. So this is for each node. Each node keeps only important field, not full text. Okay, so it will each node have node ID, okay, titles and page. You can see here unique identifier, this one, and section title, this one, page number. Okay, this is used for page, this is for page numbers. Okay, and this is used for summary, so short summary of the section. Okay, so each node contain these things, that's why it is written the node ID, title, page number and summary. Okay, summary. And here you can see if the node has children, recursively compress them. Okay, if node has children, recursively compress them. Okay, so that's why I use compress nodes, and here else otherwise it will return the empty dictionary. Okay, so in nodes. And now we are going to send the prompt to the LLM. So here this is our prompt. I'm going to send this to the LLM. So we give it to the document structure plus user query. Okay, so here we are giving document structure plus user query and ask it to pick the relevant node IDs. Okay, so here I provide the I am giving here this prompt, and here I use this json.dump compressed tree, this one. Okay, so here I'm giving this document structure here. Okay, and I'm giving here query. Okay, and here after this and after this we ask it to pick the relevant nodes. Okay, so here you can see which node ID contain the answer. Think step by step and reply only in JSON. Okay, thinking node list like this 001 002. So this is picking the answer from this section. Okay, in which section we have the answer, and here it is used for generate the response. Here you can see JSON.load response. So here you can see we have this line response. Okay, so we are going to call the LLM here. Response equals to client.chat.completion.create. With the help of this we are going to call the LLM. Okay, so here this is the model name, which model, I mean which LLM we use. I'm going to use Grok model. Okay, and this is the message, I mean send the prompt here, user and content equals to prompt, and response format in JSON. Okay, force JSON output here, and temperature equals to 0, deterministic output, no randomness. Okay, and it return this one, convert LLM JSON response. Okay, convert JSON response string into the Python dictionary. Okay, and after this we have another function 2, fetch the actual content from the PDF using the selected node IDs. Okay, so here I pass the parameter tree and node ID and pages. Okay, so this will fetch the page content from the selected node. Okay, so here this is the function name, find the nodes. Okay, so why we are going to create this function? We are creating this, why? LLM only give the node ID structure information only. Okay, so now we fetch real text from the PDF for those sections. Okay, tree, node IDs and pages, so that we can fetch the important text from the PDF. Okay, so here this is the another function. So this is the helper function. Okay, helper function to find the node inside the tree by their IDs. Okay, and we have this found equals to empty. So here we give this is the empty list, one variable. Here we can store. Okay, we store the result. Okay, for n in nodes. Okay, so here we are going to use loop in every nodes. Okay, for n in a nodes. Okay, so here you can see if current node is in selected nodes ID, keep it. Okay, and then append inside the found. We can store this node inside the found. If n dot get nodes, you can see here this line, n dot where is it? This line. Okay, so here you can see this line, if node had children. Okay, if node had children, search inside the recursively. Okay, n dot get nodes, if node had children, found dot extend find n nodes, it means children. If node has children, okay, I mean if document have section and subsection. Okay, node has children. Okay, if node has children, search inside them recursively. Okay, and then return the found. Okay, and here with the help of this node find tree, so it means get matching nodes from the tree. Okay, and result, this is the empty result that we can store the result, and here I'm going to use loop again. So this line is used for this one, pg equals to np dot get page index 1. So get the page number of this section, default 1 if missing. Okay, get the page number with the help of this, and default equals to 1 if missing. So here you can see pg equals to np dot get and page index 1. So get the page of this section, default equals to 1 if missing. Okay, and content equals to empty string means collect text from that page, and nearby page from context. And here you can see another loop. So here we are going to collect text from that page. Okay, so I use this loop 4p in range of 0 to pg minus 1. Okay, so this is the loop, and we are okay, and here we are find out the content of page and then return the here we are going to find out, I mean we are going to append in result word title and page and text content, okay, from 0 to 2000, and here return the result. Okay, here we return the result. So this line is used for what? Return the result. So 1 minute. This line used for store the result. This line store the structure result. Okay, this section are going to store the title, and this section are going to store the page number, this one. Okay, and this is going to store the content. Okay, and it has limit text size. Okay, we have 2000. Avoid the huge prompt. Okay, and this line is used for this one. Where is this page content? Where is this line, guys? Page content, this one. So this line used for add the page text. Okay, and this line is used for these two lines, this one and this one. Get the content from that page and next page. Okay, get the page number of this section. No, this is not for page, this is this one. These two lines means collect the text from the page. Okay, and after this is going to append, I mean here we are going to result inside the, sorry, we are going to append title, page number and content inside the result and return the result here. Okay, again we have third function. This is the generate the answer. Okay, final answer using the retrieval section. Here I pass the query and section. Okay, so we I mean why we create this? So we have relevant content. Now we have relevant content here. Okay, so we ask the LLM to answer only using the content. Okay, so that's why we are going to create this generate the answer. If no section, you can see here, if no section found, return early. Okay, if no section find out, return no relevant section found. Okay, otherwise it is giving us context like this. Okay, it is giving us title, page, text from the section and join them. Okay, so here build the context string from all the retrieve section. Okay, so this is giving answer here, and we use this prompt answer the question using only the context, site, section and page. Okay, here I pass the query and context. Okay, and here you can see in answer, you can see I use this. So here you can see response. Here again we are going to call the LLM to generate the final answer. So response equals to client.chat completion dot create. So with the help of this we are going to call the LLM. I use Grok model, and here we pass the message. In message we have user and content. In content prompt. Okay, and temperature equals to 0.1. Okay, 0.1 slightly creative but still controlled. Okay, and then return generated response with the help of this line. Return response return res dot choice 0 message dot content. Okay, so it is going to return the answer, generated answer. Okay, and we have this function. This is the fourth function, full pipeline, tied everything together. Okay, so here I pass the query, tree and pages. Okay, so here why we creating this is the full system. LLM find the relevant section. Here LLM find the relevant section. First LLM find the relevant section, then second we fetch their content, and third LLM generate the final answer. Okay, here you can see we have first function, LLM find the relevant section with the help of this, and in second function LLM fetch their content, and in third function LLM generate the final answer. Okay, so we use these things here. Okay, this is the full system here. Okay, here I pass query. Okay, and step 1 we are going to search. Okay, LLM select the relevant node IDs here. Okay, LLM tree, here I pass query and tree. Okay, and here node id equals to search dot get node IDs. We are going to search the node IDs. Okay, this is the empty list. Okay, and here it is print the search dot get thinking. Okay, it is going to print by using, it is going to search by using thinking from 0 to 1000, sorry, 200. Okay, so here, so the reasoning output debugging information. Okay, and selected node, it is giving us node ID. Okay, and step 2, we have selection get. So here fetch the content from those nodes. Okay, fetch the content for those nodes here. So section equals to get underscore node content. Here I pass tree and nodes ID and pages, and here it will print the title for sections. Okay, and after this it is giving us answer by using this function generate answer. Okay, so this is our generate answer function, guys. These are the function. Okay, and here print the, print the answer, and return the answer, and print the pipeline ready. Okay, so these are the function name, this is the function name, and this is also function name, get the node content. Okay, and nothing. Okay, and here you can see it is giving us pipeline ready. Okay, if I'm going to ask the question, I use answer equals to vectorless RAG. Okay, and I'm passing query, what are the key financial highlight of this report. Here I pass tree equals to tree and page equals to page. So it is, this is the query, and it is giving the answer with the help of reasoning. To find the key financial highlights of the report, we need to look for the section that discuss the financial information. Okay, and selected node, these are the nodes 004, 005 and 006. Okay, before I created nodes like this. Okay, so these are the nodes, and section we are going to find out. These are the section overview, and second one, this one, March 2024 summary. Okay, so this is find out the section and giving the answer. This is the answer. Okay, okay guys, so this is fine. LLM just find out the answer by with the help of reasoning. This is not just searching. Okay, and find out the document. Okay, so we will, it will get, it is going to take this section to pick the answer. Okay, based on reasoning, it is find out the section and giving the answer, this one. Okay, another query we are going to ask here. Okay, tree equals to tree, page equals to page, and vectorless underscore RAG. So here this is the query, and this is giving the reasoning. To find the main risk mentioned in the document, we need to look for the section that discuss potential threat or vulnerability. Okay, so these are the section selected node. Okay, and section, it is going to use this section, this one, this is the first section, second section. It is LLM now look at the section, in which section I need to find out the answer. So it took 3 section here. One, this is the 1, 2, 3 and 4. This is the 4. Okay, and give the answer from this section. Okay, so guys, this show how the reasoning based retrieval can outperform similarity based retrieval, especially for the structured document. Okay, so we replace similarity search with the reasoning here. Okay, and even though the answer wasn't perfect extracted. Okay, so here you can see the pattern is navigating the document structure instead of guessing based on a similarity. Okay, so even though answer wasn't perfect extracted, you can see the system is navigating the document structure instead of guessing based on the similarity. Okay, so like guys, this part is messy. Okay, this one. Okay, this one, this part is messy. First, we create these three things here. Okay, here LLM read the tree, this one, and then fetch the page and LLM generate the answer. Okay, so here this part is messy. Okay, you can analyze this properly. Okay, and you can take the help of any AI like Grok, Cloudy, or GPT to understand this. This is the messy, and I don't have time, and video is going to be long, so that's why I'm not explaining properly here. Okay, so if you have any doubts here, you can do Google or search. Okay, if you have any doubt. So this part is messy, otherwise everything is clean and perfect. And here I don't use page index because page index API, I don't use here page index API because it is paid, and like uh, it might be not free for you, and it is already giving us limit. Like I actually I hit one request, then it is say that you are out of credit, you need to recharge or you need to buy some credit. So that's why I have created everything manually. Okay, notes, pages, and summaries. Okay, so if you have if you don't if you have API, page index API, then it will good for you. Otherwise you can do like this. Okay, if you don't have page index API. So I use everything free. I use Grok, that is also free, and I use I have created tree manually here. Okay, okay guys, I'm going to upload this on GitHub. You can check there and find out this code. Okay,